There's something about floating in space that defies every instinct we have as humans. No up, no down. No ground beneath your feet. Just you, tethered to a spacecraft, hanging above a planet that's spinning at 1,000 miles per hour beneath you. And in that impossible place, hundreds of miles above the Earth, some of the most delicate and precise work ever attempted by human hands has taken place. This is the story of the Hubble Space Telescope repair missions, a saga that spans nearly 2 decades and 5 extraordinary journeys into orbit. It's a story about the ballet of spacewalks, the choreography of survival, and the determination to fix what many thought was unfixable. The Hubble Space Telescope wasn't just another scientific instrument. It was humanity's eye in the sky, our window into the deepest reaches of the cosmos. But that window was flawed from the moment it opened, and what followed became one of the most ambitious rescue operations ever mounted in space. Over 5 separate missions between 1993 and 2009, 32 astronauts would venture outside their spacecraft to perform intricate repairs, upgrades, and maintenance on this precious observatory. They would spend more than 165 hours spacewalking, using over 150 specialized tools, working in the darkness of orbital night to prevent thermal expansion from affecting their delicate work. This wasn't just about fixing a telescope. It was about proving that humans could work in space with the precision of surgeons, the patience of watchmakers, and the courage of explorers. Every spacewalk was a carefully choreographed dance, rehearsed hundreds of times in massive water tanks on Earth, where astronauts in pressurized suits practiced every twist of every bolt, every cable connection, every instrument swap. The stakes couldn't have been higher. One mistake, one dropped tool, one moment of carelessness could doom not just the mission but the entire future of space-based astronomy. Let's go back to where it all began, long before the first repair mission ever launched. Because to understand why these spacewalks mattered so much, you need to understand the dream that created the Hubble Space Telescope in the first place. The idea of putting a telescope in space wasn't new when the Hubble Space Telescope launched in 1990. In fact, the concept had been floating around scientific circles for decades. The father of this dream was Lyman Spitzer Jr., an astronomer at Princeton University who, in 1946, wrote a paper titled Astronomical Advantages of an Extraterrestrial Observatory. World War II had just ended, and the German V-2 rockets had proven that reaching space was possible. Spitzer realized something profound: if you could get a telescope above Earth's atmosphere, you could see the universe with a clarity that ground-based telescopes could never achieve. Spitzer wasn't just dreaming idly. He laid out specific technical arguments for why a space telescope would revolutionize astronomy. He understood that Earth's atmosphere, while essential for life, was a nightmare for astronomers trying to peer into the depths of space. The atmosphere is always moving, always churning with temperature differences that create turbulence. Hot air rises from the ground during the day. Wind shears create layers of air moving at different speeds. Weather systems churn moisture and particles through the sky. All of this movement causes starlight to dance and shimmer as it passes through, creating the twinkling effect that poets love but astronomers despise. Beyond just the turbulence, the atmosphere actively blocks certain types of light from ever reaching the ground. Ultraviolet radiation, which could tell us about the hottest stars and most energetic cosmic phenomena, gets absorbed high in the atmosphere by ozone. Certain infrared wavelengths, which reveal cool objects like dust clouds where stars are forming, get blocked by water vapor. X-rays and gamma rays from violent cosmic events never make it through at all. An astronomer on Earth is like someone trying to understand the world while looking through a dirty, wavy window that only lets certain colors through. Spitzer understood that getting above that window would open up entire new realms of astronomy. Think about what the atmosphere does to starlight. Every photon that travels billions of years across space, carrying information about distant galaxies and dying stars, has to pass through miles of turbulent air before it reaches a telescope on Earth. The atmosphere wobbles and shimmers. It absorbs certain wavelengths of light completely. It scatters others. That's why stars twinkle when you look up at night. That romantic shimmer is actually the atmosphere distorting the light, bending it this way and that as pockets of warm and cool air move around. For astronomers trying to study the universe in precise detail, it's like trying to read a book through a swimming pool while someone's doing cannonballs into the water. Ground-based observatories tried everything they could to minimize atmospheric interference. They built telescopes on mountaintops, above as much of the atmosphere as possible. Places like Mauna Kea in Hawaii, at nearly 14,000 feet elevation, became prime real estate for observatories because the air there was thin and stable. They chose sites in deserts like Chile's Atacama Desert, where the air was exceptionally dry and cloud cover was minimal. They developed clever techniques called adaptive optics that used flexible mirrors to compensate for atmospheric distortion in real time, essentially making the telescope's mirror wiggle to cancel out the atmosphere's wiggling. But there were fundamental limits to what these techniques could achieve. You could never completely eliminate the atmosphere's effects. You could never observe in wavelengths that the atmosphere blocked entirely. And you could never escape the fact that even on the clearest night, from the best mountaintop observatory, you were still looking through miles of air that was constantly moving and changing. Spitzer understood that a telescope in space would be free from all of that. It could observe in wavelengths that never reach Earth's surface, like ultraviolet and certain infrared frequencies. It could take long exposures without atmospheric distortion blurring the images. It could see farther, clearer, and more precisely than any telescope ever built. It could point at a target and stare at it for hours or even days without the target setting below the horizon or clouds rolling in to block the view. It would have a stability and consistency that ground-based telescopes could only dream of. But in 1946, this was pure science fiction. The technology didn't exist. The rockets weren't powerful enough to lift a large telescope into orbit. The electronics weren't sophisticated enough to control and operate a complex observatory remotely from the ground. The solar panels that would be needed to power such a telescope in space hadn't been invented yet. The communication systems that would be required to send commands up and receive data back didn't exist in anything close to the form they would need. And the money, well, nobody was ready to spend what would likely be billions of dollars on a space telescope when they were still rebuilding from a world war and trying to figure out what this new space age even meant. But Spitzer didn't give up on his dream. He spent decades advocating for a large space telescope, writing papers, giving presentations, convincing other scientists and eventually politicians that this was worth pursuing. He became the project's most tireless champion, speaking at conferences, testifying before congressional committees, building support within the scientific community. By the 1960s, NASA was seriously considering the concept. The Apollo program had proven that ambitious space projects could succeed. The technology was advancing rapidly with each new spacecraft, each new mission. And astronomers were becoming more vocal about the limitations of ground-based observatories, more insistent that space was the future of astronomy. The path from Spitzer's vision to an actual space telescope was long and politically complicated. In the early 1970s, NASA proposed building a 3-meter diameter space telescope, significantly larger than what would eventually become Hubble. The agency presented ambitious plans showing how such a telescope could revolutionize our understanding of the universe. But Congress was skeptical. The Vietnam War was draining national resources. The public was growing weary of expensive space projects after the excitement of the moon landings had faded. Why spend billions on a telescope when there were problems to solve on Earth? NASA heard these objections over and over in budget hearings. NASA had to scale back its ambitions, reducing the proposed mirror size from 3 meters to 2.4 meters. This size was chosen partly for scientific reasons. It was the minimum size that would still provide a major leap in capability over ground-based telescopes. But it was also chosen for practical reasons. The 2.4-meter diameter matched the spy satellite mirrors that the military-industrial complex already knew how to manufacture for classified reconnaissance satellites. The tooling and expertise existed. The manufacturing processes were proven, even if they were secret. This meant the mirror could be made more reliably and potentially at lower cost. Even with the reduced size, funding was still uncertain. The project faced cancellation multiple times throughout the 1970s. NASA enlisted the help of the astronomy community to lobby Congress. Prominent astronomers testified about the revolutionary science a space telescope could enable. They talked about being able to see back to the early universe, to watch galaxies forming in the cosmic dawn just a few 100 million years after the Big Bang. They described how the telescope could study the atmospheres of planets around other stars, potentially discovering signs of life elsewhere in the galaxy. They explained how it could measure the expansion rate of the universe with unprecedented precision, helping to determine whether the universe would expand forever or eventually collapse back in on itself. They painted a picture of discovery that was compelling enough to keep the project alive through numerous budget battles and political challenges. The European Space Agency became a critical partner in the mid-1970s. ESA agreed to contribute 15% of the funding in exchange for guaranteed observing time for European astronomers. This international collaboration not only provided crucial financial support but also gave the project additional political protection. It wasn't just an American telescope anymore. It was representing the scientific aspirations of the Western world. Canceling it would mean breaking international commitments and damaging relationships with key allies. This political reality probably saved the project during some of its most vulnerable moments. The formal design and construction phase began in earnest in the late 1970s. NASA partnered with PerkinElmer Corporation to build the mirrors and optical system. Lockheed was contracted to build the spacecraft structure and systems. Marshall Space Flight Center in Huntsville, Alabama, took the lead on managing the overall project. Goddard Space Flight Center in Maryland would operate the telescope once it was in orbit. The project involved thousands of engineers, technicians, and scientists working across the country. The telescope would have a primary mirror 2.4 meters in diameter, nearly 8 feet across. This mirror would collect light and focus it toward a smaller secondary mirror, which would then reflect the light back through a hole in the primary mirror to the scientific instruments located behind it. The entire optical system had to be aligned with extraordinary precision. The telescope would orbit about 300 miles above Earth, well clear of the atmosphere but still close enough for the space shuttle to reach for servicing missions. At that altitude, it would complete one orbit every 95 minutes, traveling at a speed of about 17,000 miles per hour. The design process was extraordinarily complex. The telescope had to be sensitive enough to detect faint light from objects billions of light-years away, yet robust enough to survive launch vibrations, temperature extremes, and years of exposure to the space environment. It needed pointing accuracy measured in millionths of a degree, the equivalent of being able to hold a laser pointer steady on a dime 200 miles away. If it couldn't point accurately and hold that pointing, all that optical perfection would be wasted. It needed power systems that would work reliably for decades without maintenance. It needed communication systems that could beam gigabytes of data back to Earth from its high orbit. Every component, from the largest mirror to the smallest circuit, had to be designed and tested to space-worthy standards. The primary mirror was arguably the most critical component. It had to be polished to a smoothness where the highest peak and lowest valley differed by no more than a millionth of an inch. To put that in perspective, if the mirror were scaled up to the size of the continental United States, the highest mountain on that scaled-up surface would be only 6 inches tall. Achieving this level of precision required months of careful grinding and polishing, checking and rechecking the mirror's shape with sophisticated testing equipment. The mirror was made of ultra-low expansion glass, a special type of glass that wouldn't change shape with temperature variations. Normal glass expands when heated and contracts when cooled. Even tiny thermal expansions would distort the mirror's shape enough to ruin the telescope's focus. The ultra-low expansion glass used for Hubble's mirror had thermal expansion properties about 1/100th that of ordinary glass. After the blank was cast and the basic shape was ground, the polishing process began. Using progressively finer abrasives, technicians polished the mirror surface to its final shape, removing material measured in millionths of an inch with each polishing run. After polishing, the mirror was coated with a microscopically thin layer of aluminum to make it reflective. Aluminum was chosen because it reflects visible and ultraviolet light well, which was important for Hubble's science goals. The aluminum layer, only a few atoms thick, was applied in a vacuum chamber to ensure purity and uniformity. Then the aluminum was overcoated with an even thinner layer of magnesium fluoride. This protective overcoat prevented the aluminum from oxidizing and also enhanced its reflectivity in ultraviolet wavelengths. The telescope's structure had to be incredibly stable. Any flexing or vibration would blur the images. The tiniest movement of the mirror relative to the instruments would smear out the light from distant stars, ruining observations that might have taken hours to complete. Engineers designed a graphite epoxy truss that was stiff yet lightweight. This truss had to be strong enough to hold the mirrors in precise alignment even as the telescope moved from the heat of direct sunlight, where temperatures could exceed 250 degrees Fahrenheit, to the cold of Earth's shadow, where temperatures would plunge to minus 250 degrees. That's a 500-degree temperature swing happening over the course of minutes every single orbit. The structure had to handle these extremes without bending, twisting, or changing shape in any way that would affect the optical alignment. This structure had to support not just the mirrors but also the 5 scientific instruments that would analyze the light the mirrors collected. These instruments included cameras to take pictures, spectrographs to split light into its component wavelengths, and photometers to measure light intensity precisely. Each instrument was a sophisticated piece of equipment that had taken years to develop and millions of dollars to build. The structure also had to support the guidance sensors that would keep the telescope pointed accurately, the gyroscopes that would measure any rotation, and all the electronics and systems that would keep everything running. But here's what made Hubble truly unique in the history of space telescopes: it was designed from the very beginning to be serviced by astronauts. This was revolutionary. Previous satellites and space probes were launched and then left alone. If something broke, that was it. Mission over. The satellite might limp along with reduced capability, or it might fail completely. Either way, there was nothing anyone could do about it except watch helplessly from the ground. But Hubble would be different. It would have handrails installed around its exterior for astronauts to grip while they worked. It would have equipment bays with doors that could be opened in space using standard tools. Its instruments would be modular, designed to slide in and out on rails like drawers in a filing cabinet. Every bolt that might need to be turned during a servicing mission was positioned where a spacewalker could reach it. Every electrical connector was sized and designed to be operated by someone wearing thick, pressurized gloves. The entire telescope was built around the idea that humans would periodically visit it, fix whatever needed fixing, and upgrade it with new technology as that technology became available. This serviceability wasn't just a nice feature, it was a fundamental requirement driven by practical considerations. Space telescopes are expensive, phenomenally expensive. Development costs run into the billions of dollars. Launch costs add hundreds of millions more. If you spend $2 billion to build and launch a telescope, you want it to last as long as possible and to be able to take advantage of technological improvements as they emerge. In the late 1970s, when Hubble was being designed, electronics were advancing rapidly. The instruments and detectors that were state-of-the-art in 1978 might be obsolete by the time the telescope launched in the mid-1980s. And they would certainly be outdated within a few years after that. By making the telescope serviceable, NASA ensured that it could be upgraded with whatever new technology emerged, extending its useful life potentially for decades. The initial plan called for servicing missions every few years, with astronauts replacing failed components, upgrading instruments, and performing preventive maintenance. The telescope was designed with an operational lifetime of 15 years, with the possibility of extending that through regular servicing. This was an unprecedented approach for a space telescope, but it made enormous economic and scientific sense. The serviceability requirement influenced every aspect of Hubble's design. Connectors had to be sized and positioned so that a gloved hand could reach them and operate them. This meant larger connectors than might otherwise be used, with generous tolerances to allow for the imprecision of working in bulky gloves. Bolts had to be accessible and turn in directions that a spacewalker could manage. You couldn't have a bolt head tucked into a tight corner where a tool couldn't reach, or oriented so that turning it would require an awkward wrist angle. Instruments had to slide in and out on rails with smooth, reliable mechanisms that would work even after years in space. The rails had to be robust enough to guide equipment weighing hundreds of pounds, yet precise enough to ensure proper alignment of delicate optical components. Everything had to be built with the assumption that someday, an exhausted astronaut floating in microgravity would need to work on it, possibly in an emergency, possibly with damaged or improvised tools. Engineers had to imagine themselves in spacesuits, working in the dark, with limited time and limited dexterity, and design accordingly. This design philosophy, this commitment to making Hubble serviceable by humans, would prove to be the most important decision ever made about the telescope, because without it, the entire project would have been a complete failure after what happened next. April 24, 1990. After years of delays, budget overruns, and technical challenges that sometimes seemed insurmountable, the Space Shuttle Discovery finally lifted off from Kennedy Space Center carrying the Hubble Space Telescope in its cargo bay. The telescope that had cost over $2 billion to develop and build, that represented decades of planning and hoping, was finally heading to orbit. The launch had been delayed multiple times. Originally scheduled for October 1986, it was pushed back after the Challenger disaster in January of that year, when the shuttle exploded 73 seconds after liftoff, killing all 7 crew members. The entire shuttle fleet was grounded for nearly 3 years while NASA investigated the accident and redesigned the solid rocket boosters that had caused the catastrophic failure. Hubble sat in storage at Lockheed's facility in Sunnyvale, California, a completed telescope waiting for its ride to space. Engineers worried about how the extended delay might affect its delicate systems. Electronics can degrade over time. Mechanisms can stick if not used. Materials can age in unpredictable ways. The telescope was maintained as carefully as possible during the layover, powered up periodically, systems checked and rechecked. But there was always a nagging concern that something might have degraded during the long wait. When Discovery finally lifted off in April 1990, carrying astronauts Lauren Shriver as commander, Charles Bolden as pilot, and mission specialists Stephen Hawley, Bruce McCandless, and Catherine Sullivan, there was a palpable sense of relief mixed with the usual anxiety of a shuttle launch. The telescope had been waiting too long. The astronomy community had been waiting too long. Careers had been put on hold waiting for this telescope. Young graduate students who had started their studies expecting to use Hubble data were now finishing their PhDs without it. Senior astronomers who had helped design the telescope were worried they might retire before it ever launched. It was time, past time really, to finally get this observatory into orbit and start the science it was designed to perform. The deployment itself was an anxious operation that took place the day after launch. The telescope weighed 24,000 pounds and was over 43 feet long, roughly the size of a large school bus. It completely filled the shuttle's cargo bay. Getting it out safely required precision and patience. Stephen Hawley, operating the shuttle's robotic arm from the aft flight deck, moved with extreme caution. The arm had to grapple Hubble using a special fixture, then slowly lift it up and out of the cargo bay. Any sudden movement could damage the delicate instruments or shake the telescope hard enough to misalign its optics. Every astronaut on board felt the weight of the moment. This wasn't just another satellite deployment. This was humanity's best eye into the cosmos, the product of decades of planning and billions of dollars. If something went wrong during deployment, if the telescope was damaged or couldn't be released properly, it would be a disaster of epic proportions. Hawley lifted Hubble slowly, centimeter by centimeter, watching his displays intently as the arm's joints articulated. The telescope rose up out of the cargo bay, its solar array still folded against its body, its golden skin catching the sunlight. When it was high enough, the shuttle performed a careful maneuver to orient both spacecraft properly for release. Then, at the planned moment, Hawley commanded the arm to release its grip. Hubble floated free, separating from the shuttle and beginning its independent orbit. There was applause in mission control and aboard the shuttle, but also an underlying tension that wouldn't fully release until the telescope proved it could work. The real test would come when the telescope opened its eye and looked at the stars. The initial checkout period involved systematically powering up each of Hubble's systems and verifying they worked as expected. The solar arrays deployed properly, their golden panels unfolding like enormous wings and locking into place. The arrays began generating power immediately, soaking up sunlight and converting it to electricity to run the telescope's systems. The communication systems linked up with ground stations, establishing the data connection that would allow the telescope to send observations back to Earth. Engineers monitored telemetry streams, checking thousands of individual data points to ensure everything was functioning correctly. The guidance system activated, a critical moment because without accurate pointing, the telescope would be useless. 6 gyroscopes spun up, their precision-machined rotors spinning at thousands of revolutions per minute. These gyros would measure any rotation of the telescope, allowing the control system to detect and correct unwanted drift. Star trackers, specialized cameras that could recognize patterns of bright stars, locked onto guide stars and provided absolute position information. The system used this information to figure out exactly where the telescope was pointing and to hold that pointing with extraordinary stability. Initial tests showed that the pointing system was working well. The telescope could point itself at targets and hold that pointing steady enough that stars appeared as sharp points even in long exposures. This was exactly what was needed. Everything seemed to be working. The telescope could point itself at targets with great precision. It could record data and send it back to Earth. The solar arrays were generating plenty of power. The communications were solid. From an engineering standpoint, the deployment appeared successful. All the systems that had been tested on the ground seemed to be working just as well in space. The excitement in the astronomical community was electric. Finally, after decades of dreaming and years of building and months of delays, humanity had a great observatory in space. The first images were scheduled to be released about a month after launch, once the telescope had been fully checked out and calibrated. Scientists around the world waited eagerly to see what Hubble would reveal. There were plans to observe distant galaxies, to study star-forming regions in spectacular nebulae, to examine planets in our own solar system with unprecedented clarity. Hundreds of astronomers had prepared observing proposals years in advance, competing for precious time on the telescope. Every proposal had been peer-reviewed by committees of experts who judged which observations were most scientifically valuable. The expectations were enormous. This telescope was going to change astronomy, opening new windows on the universe that had been closed to ground-based observatories. And then came the devastating news. The first test images that came back from Hubble in early May showed that something was terribly wrong. The images were blurry, not just slightly out of focus, but significantly degraded. Stars that should have appeared as sharp pinpoints were surrounded by fuzzy halos. The telescope that was supposed to see 10 times more clearly than ground-based observatories was producing images that looked worse than what many Earth-based telescopes could achieve. The finest details that Hubble was supposed to reveal were smeared out and invisible. Engineers and scientists at the Space Telescope Science Institute and at NASA immediately began investigating. This couldn't be just a focusing problem, could it? The telescope had focusing mechanisms that could adjust the position of the secondary mirror to find the optimal focus. They commanded Hubble to run through its full focus range, taking images at different positions. But no matter where they set the focus, the images stayed blurry. There was improvement at one particular focus position, but even at the best focus, the images were far from what they should be. The investigation team commanded Hubble to focus on bright stars and analyzed the patterns in the resulting images carefully. They looked at how the light from a star was distributed across the detector, studying the shape and intensity of the fuzzy halo around each star. These patterns contained information about what was wrong with the optical system. Using sophisticated computer models, they could work backward from the observed light patterns to figure out what kind of optical defect would produce those patterns. What they discovered made their heart sink. The telescope's primary mirror, that 2.4-meter piece of precisely polished glass that had taken years to manufacture and that was supposed to be the most perfect large mirror ever made, had been ground to the wrong shape. The error was tiny in absolute terms, but catastrophic in its effects. The outer edge of the mirror was too flat by about 1/50th the thickness of a human hair, a microscopic error of approximately 2,200 nanometers. In the world of precision optics, this tiny deviation was absolutely catastrophic. It meant that the mirror couldn't bring all the light to a single perfect focus point. Instead of converging rays of light from a distant star to a sharp point, the mirror created what's called spherical aberration. Light reflecting from the center of the mirror focused at one point, while light from the edges focused at a slightly different point. The result was that instead of a sharp stellar image, you got a bright core surrounded by a fuzzy halo. For the ultra-precise work Hubble was designed to do, studying faint objects near bright ones or resolving fine details in distant galaxies, this was absolutely disastrous. The public reaction was swift and brutal. Late-night comedians made jokes about NASA's $2 billion blurry telescope. Jay Leno quipped that Hubble had Coke bottle glasses. Saturday Night Live did sketches mocking the telescope. News headlines called it a national embarrassment and a symbol of government waste. Members of Congress held hearings and demanded investigations. How could this have happened? How could NASA have spent so much money and so many years building this telescope, subjected it to so many reviews and tests, only to launch it with a fundamental flaw in its primary mirror? The agency that had put men on the moon, that had pioneered space exploration, had somehow messed up the most basic component of a telescope. The investigation into how the error occurred revealed a story of cascading failures and missed opportunities that was almost as troubling as the mirror flaw itself. The mirror had been polished by PerkinElmer Corporation using a special testing device called a null corrector. This device was supposed to guide the polishing process by measuring the mirror's shape and telling the technicians whether they needed to remove more material from certain areas. The null corrector used a beam of light to test the mirror. If the mirror had exactly the right shape, the null corrector would produce a certain pattern. Any deviation from the perfect shape would show up as a distortion in that pattern. But the null corrector itself had been incorrectly assembled during its construction at PerkinElmer. One of its optical elements, a small lens, was positioned 1.3 mm out of place, about the width of a paperclip wire. This tiny positioning error in the test equipment meant that the null corrector was giving false readings. It was telling the technicians that the mirror had the right shape when actually it was being polished to the wrong shape. The technicians, trusting their test equipment, polished the mirror based on what the null corrector told them. They did their job with extraordinary precision and care. They followed all their procedures. But they were following a test device that was lying to them. What made this even more tragic was that there had been warning signs during the mirror's construction that something might be wrong. Alternative testing methods, using different equipment and different optical principles, had suggested that the mirror shape didn't match what the null corrector was indicating. But when these conflicting results were discovered, the null corrector measurements were trusted more. The null corrector was the primary test device, specifically designed for this mirror. The alternative tests were considered less accurate. So the conflicting results were noted, discussed in meetings, but ultimately dismissed as probably being errors in the alternative test methods rather than errors in the null corrector. The error had been literally built into the mirror, polished in with meticulous precision. Perkin-Elmer had created a perfectly wrong shape, a mirror that was exactly what the faulty null corrector specified but not what the telescope needed. And because everyone trusted their test equipment, because the null corrector readings were consistent and precise, nobody caught the error before the mirror was installed in the telescope and the telescope was launched. The investigation, led by the Hubble Independent Optical Review Panel, found multiple contributing factors. Perkin-Elmer's management structure had been confusing, with responsibilities unclear and communication between groups inadequate. The company had not adequately supervised the construction of the null corrector, allowing the assembly error to go undetected. When alternative test results conflicted with the null corrector, there had been no rigorous process to resolve the discrepancy. NASA's oversight had also been insufficient. The agency had trusted Perkin-Elmer's expertise and had not insisted on independent verification of the mirror using different test methods. It was a failure of quality control, a failure of communication, and a failure of skepticism at multiple levels. For months after the flaw was discovered, there was serious debate about what to do. The situation seemed almost hopeless. The mirror was in space, permanently installed in the telescope. You couldn't just remove it and replace it. The mirror itself was the structural heart of the telescope. Everything else was built around it. Some engineers and scientists argued that Hubble should be brought back to Earth in the shuttle's cargo bay, the mirror replaced with a correctly shaped one, and the telescope relaunched. But the logistics of this were daunting. It would take years to build a new mirror. The costs would be enormous. And there was no guarantee that a second attempt would be successful. Others suggested abandoning Hubble entirely and building a new telescope from scratch. Start over with better quality control and more independent verification. Learn from the mistakes and build it right the next time. But this option was even more expensive and would take even longer. The astronomers who had been waiting for Hubble would have to wait another decade or more. The political and public support for such a project after this very public failure seemed unlikely. NASA was facing a crisis of confidence. The agency's reputation, already damaged by the Challenger disaster, was taking another hit. Critics questioned whether NASA could still execute complex projects successfully. The future of the entire space astronomy program seemed to hang in the balance. If NASA couldn't fix this, if Hubble became a permanent embarrassment orbiting uselessly overhead, it would affect funding and support for all future space telescopes and possibly for human spaceflight as well. But remember that crucial design decision made years earlier: Hubble had been built to be serviced in orbit. Engineers began exploring a different option, one that seemed impossible at first but gradually came to look like the best hope. What if they couldn't fix the mirror itself, but they could fix what the mirror did to the light? What if they could build corrective optics, essentially space glasses for the telescope, that would intercept the light from the flawed mirror and bend it back to where it should be? The physics of this approach were actually straightforward. If you knew exactly how the mirror was misshaped, you could calculate exactly how that misshape affected the light paths. Then you could design additional mirrors to correct those light paths. It was like using eyeglasses to correct for a vision problem. Your eye might have the wrong shape, but the glasses bend the light so that it ends up in the right place anyway. The same principle could work for Hubble. Of course, the devil was in the details. The corrective optics would have to be manufactured to incredibly precise specifications. The same level of precision that had been required for the primary mirror would be needed for these corrective mirrors. And they would have to be installed by astronauts working in the unforgiving environment of space, positioned correctly to within a millimeter or less. It would require removing one of Hubble's instruments to make room for the corrective optics package. And it would demand spacewalks of unprecedented complexity and duration. But it was possible. And that possibility, that glimmer of hope, became the foundation for what would become one of the most famous space missions in history, the first Hubble servicing mission, STS-61. The telescope that many had written off as a failure was going to get a second chance. And the astronauts who would provide that second chance were about to begin the most intensive training program in NASA's history. The decision to attempt a repair mission was made, but turning that decision into reality would take nearly 3 years of intensive preparation. This wasn't like previous spacewalks, where astronauts performed relatively straightforward tasks like testing equipment or deploying antennas. This was going to be surgery in space, performed on humanity's most complex and expensive orbital observatory. It would push the limits of what humans could do while wearing pressurized suits and floating in microgravity. The first challenge was designing the corrective optics. Engineers at NASA and the Space Telescope Science Institute worked around the clock to create a device they called COSTAR, which stood for Corrective Optics Space Telescope Axial Replacement. The name was carefully chosen to be pronounceable and to create an acronym that suggested restoration and correction. COSTAR was essentially a shoebox-sized package containing 5 pairs of small corrective mirrors, each about the size of a coin. These mirrors would be positioned in the light path inside the telescope. They would intercept light from Hubble's flawed primary mirror and bend it using precisely curved surfaces to correct the spherical aberration before the light reached Hubble's scientific instruments. Designing COSTAR required extraordinary precision. The engineers had to first determine exactly how the primary mirror was misshaped, down to nanometer-level detail. Then they had to calculate precisely what shape the corrective mirrors needed to be to compensate for that error. Then they had to figure out how to manufacture those corrective mirrors to the required precision. And finally, they had to package all of this into a unit that could fit into one of Hubble's instrument bays, that could survive launch vibrations and the space environment, and that could be installed by astronauts wearing thick gloves. But COSTAR alone wouldn't be enough to completely fix Hubble's vision problem. COSTAR would correct the light going to 3 of Hubble's instruments, the Faint Object Spectrograph, the Faint Object Camera, and the Goddard High-Resolution Spectrograph. But Hubble's Wide Field and Planetary Camera, one of its primary instruments and the one that would produce most of the beautiful images that would eventually make Hubble famous, would still receive uncorrected light directly from the flawed primary mirror. COSTAR couldn't help the Wide Field Camera because of how the light paths were arranged inside the telescope. So NASA commissioned the construction of a replacement camera, the Wide Field and Planetary Camera 2, or WFPC-2, pronounced with PIC-2 by the astronauts and engineers. This new camera would be essentially identical to the original camera in terms of its external dimensions and how it mounted to the telescope, but it would have its own corrective optics built right into it. Small mirrors inside WFPC-2 would compensate for the primary mirror's spherical aberration, allowing the camera to produce sharp images even when receiving light from the flawed primary mirror. Building WFPC-2 required an incredible rush effort. The Jet Propulsion Laboratory in Pasadena, California, which had built the original camera, took on the challenge of designing and building the replacement in just 3 years. This was an extraordinarily short timeline for such a complex instrument. Every component had to be designed, manufactured, tested, and integrated. The corrective optics had to be calculated with extreme precision and then manufactured and tested to ensure they would work correctly. The entire instrument had to fit exactly into the space occupied by the original camera, using the same mounting points and electrical connections. And it all had to be completed in time for the planned repair mission in December 1993. Installing COSTAR meant removing one of Hubble's existing instruments to make room for it. The instrument chosen for removal was the high-speed photometer, a device designed to measure rapid changes in the brightness of astronomical objects. It was a scientifically valuable instrument, and many astronomers had planned observations using it. Seeing it sacrificed was painful for the scientific community. But there was simply no alternative. Hubble didn't have room for both the high-speed photometer and COSTAR, and correcting the telescope's vision took priority over any single instrument. The high-speed photometer would be removed and returned to Earth, where it would eventually end up in museums as a relic of Hubble's early, troubled days. While engineers designed the hardware, NASA began selecting and training the crew who would perform the repair. The selection process was rigorous. The agency needed astronauts with extensive EVA experience who could handle the physical and mental demands of performing 5 consecutive days of spacewalks. They needed people who could work well together under pressure, who could troubleshoot problems on the fly, and who had the patience and precision to perform delicate tasks while wearing bulky suits and working in extreme conditions. 7 astronauts were chosen for the mission: Richard Covey as commander, Kenneth Bowersox as pilot, and 5 mission specialists: Story Musgrave, Catherine Thornton, Jeffrey Hoffman, Thomas Akers, and Claude Nicolia. Covey and Bowersox would fly the shuttle and manage the spacecraft systems while the others performed the repairs. 4 of the mission specialists, Musgrave, Thornton, Hoffman, and Akers, would perform the spacewalks in 2 teams of 2. Nicolia, a Swiss astronaut representing ESA, would operate the shuttle's robotic arm, positioning spacewalkers and managing Hubble during the repair work. Story Musgrave was chosen as the lead spacewalker. At 58 years old, he would be the oldest person to perform a spacewalk to that date. But his age came with incredible experience. This would be his 6th space flight, and he had more EVA experience than almost anyone else in the astronaut corps. Musgrave had degrees in mathematics, chemistry, medicine, literature, operations research, and physiology. He was known for his meticulous approach to preparation and his insistence on understanding every detail of every system he would touch. If anyone could lead this monumentally complex repair mission, it was Story Musgrave. Catherine Thornton would serve as Musgrave's partner on 3 of the 5 spacewalks. She had flown in space twice before and had performed EVA on her previous mission. Thornton was known for her calm demeanor under pressure and her systematic approach to problem solving. She and Musgrave would form one spacewalking team. Jeffrey Hoffman and Thomas Akers would form the second team. Hoffman, a former high-energy astrophysicist, had flown 3 previous shuttle missions and had performed 1 previous spacewalk. He understood the science behind Hubble better than most astronauts, which would prove valuable when making decisions about the repairs. Akers, like Thornton, had flown twice before and had EVA experience. He was known for his physical strength and his ability to keep working effectively even when exhausted. The crew would train for nearly a year, but it wasn't a normal year of training. Most shuttle missions might spend a few months training, with perhaps 20 to 30 hours of underwater practice in the neutral buoyancy laboratory. The STS-61 crew would spend over 300 hours in the water tank, practicing every single task they would perform in space, over and over until the movements became automatic. This mission would require 5 spacewalks over 5 consecutive days, something that had never been attempted before. Previous shuttle missions had done at most 3 EVAs, and they were typically spread out over the mission with rest days in between. But the Hubble repair would be different. The shuttle could only stay in orbit for about 11 days with the consumables it could carry. That meant the EVAs had to happen quickly, 1 per day for 5 days straight, with only nighttime hours for rest in between. Each spacewalk would last between 6 and 8 hours. The astronauts would be working with tools and equipment that didn't exist when training began, tools that were being invented and refined even as the crew practiced. NASA built full-scale mock-ups of the Hubble Space Telescope and placed them in the Neutral Buoyancy Laboratory at the Marshall Space Flight Center in Huntsville, Alabama. This facility had a water tank large enough to submerge a full-scale Hubble mock-up along with spacewalkers and their support divers. By carefully adding weights to their spacesuits, technicians could adjust each astronaut's buoyancy until they were perfectly neutral, neither sinking nor floating. In this state, the astronauts could simulate the sensation of floating in microgravity, though it wasn't a perfect simulation. Water has drag that space doesn't have, and movements underwater feel different from movements in vacuum. But it was the best training method available, and it allowed astronauts to practice complex tasks for hours at a time while wearing full spacesuits. Hour after hour, day after day, the crew practiced every step of the planned repairs. They rehearsed opening equipment bay doors, disconnecting electrical cables, removing instruments, installing replacements. Each task was broken down into individual steps, and each step was practiced until it could be performed smoothly and reliably. The underwater practice sessions were exhausting. A typical session might last 6 to 8 hours, matching the planned duration of the actual spacewalks. By the end of a session, the astronauts would be physically drained. Their hands would be cramped and sore from squeezing the stiff gloves for hours. Their shoulders and arms would ache from fighting the suit's resistance to movement. But they kept going, because they knew that in space, there would be no second chances, no do-overs. Story Musgrave approached the training with an intensity that became legendary among the crew. He insisted on practicing every procedure until it became second nature, until the movements flowed automatically even when wearing bulky pressure suit gloves that made fine motor control nearly impossible. He would stay late after training sessions, studying technical drawings, memorizing the location of every bolt and every connector on the telescope. He wanted to be able to work by feel if necessary, to know instinctively where everything was located even in the darkness of orbital night. Musgrave also insisted on understanding not just how to do each task but why it needed to be done in a particular way. He wanted to know the engineering rationale behind every procedure so that if something went wrong, if a procedure couldn't be completed as planned, he would understand enough to improvise a solution. This deep understanding would prove crucial during the actual mission when unexpected problems arose. The tools themselves were marvels of engineering. Over 150 specialized tools were developed for the mission. Some were modified versions of existing tools, adapted for use in space. Others were completely new inventions, created specifically for Hubble servicing. There was the pistol grip tool, a battery-powered device that could drive bolts with precise torque settings while the astronaut floated untethered in space. The tool had multiple torque settings that could be selected to match the requirements of different bolts. Too much torque could strip threads or crack components. Too little wouldn't secure things properly. The pistol grip tool took the guesswork out of tightening bolts in space. There were custom wrenches, each sized for specific bolts on Hubble. There were foot restraints that would anchor astronauts to the robotic arm or to the telescope itself, giving them a stable platform to work from. These weren't simple toe loops. They were sophisticated mechanical devices that could be adjusted to fit each astronaut's boots securely, with redundant locking mechanisms to ensure they wouldn't accidentally release. An astronaut in a foot restraint had a solid foundation to push against, allowing them to apply significant force to stuck bolts or resistant mechanisms without spinning out of control. There were tether systems to prevent tools from floating away into space. Every tool had an attachment point where a tether could be clipped. The tethers themselves were carefully designed. They had to be strong enough to hold a tool securely but flexible enough not to interfere with the astronaut's movements. They had to be long enough to allow the tool to be used comfortably but short enough not to tangle with other tethers or snag on equipment. Managing tethers during a spacewalk was a constant challenge. With dozens of tools, each on its own tether, the spacewalker had to maintain constant awareness of where everything was to prevent a tangled mess that could waste precious time. Every tool had to work in the temperature extremes of space, where sunlight could heat surfaces to over 250 degrees Fahrenheit while shadowed areas plunged to -250 degrees. The tools had to function in a vacuum, where lubricants can evaporate and materials can cold weld together. They had to be used by an astronaut wearing gloves that reduced tactile sensation to almost nothing. You couldn't feel fine textures or small details through the gloves. Everything had to be done by visual feedback and by learning to sense large-scale forces and resistances. The mission plan called for the spacewalks to be conducted during orbital night, when Hubble would be in Earth's shadow. This wasn't for the astronauts' comfort. In fact, working in complete darkness would make everything more difficult. The reason was thermal management. In direct sunlight, Hubble's aluminum structure would heat up and expand. Different components would expand by different amounts depending on their material and their exposure to sunlight. This thermal expansion, though small in absolute terms, could cause misalignments in the telescope's precise optical systems. It could also cause bolts to bind or mechanisms to stick. By working in darkness, the astronauts could ensure that the telescope was thermally stable. Everything would be cold, uniformly cold, contracted as much as it was going to contract. Instruments would slide in and out of their bays more smoothly. Bolts would thread more reliably. Alignment pins would fit into their holes. The trade-off was that the astronauts would be working by the light of helmet-mounted lamps, creating harsh shadows that could hide crucial details. But NASA's engineers determined that the benefits of thermal stability outweighed the difficulties of working in the dark. Working in complete darkness 300 miles above Earth, wearing a bulky spacesuit, manipulating tiny screws and delicate electronics with gloved hands, this was the challenge the crew trained for. They practiced by feel, memorizing the location of every bolt and latch. They learned to work by the light of helmet-mounted lamps, which created harsh shadows and made depth perception difficult. They learned to trust their partners, to communicate constantly, to work as a seamlessly coordinated team even when they couldn't easily see each other. The mission simulations were incredibly detailed and realistic. NASA conducted 7 complete end-to-end simulations of the entire mission, including all 5 spacewalks. This was unprecedented. Most shuttle missions might do 2 or 3 full simulations. But for STS-61, NASA wanted to be absolutely certain that nothing had been overlooked, that every possible scenario had been considered and practiced. Each full simulation took over a week to complete and involved hundreds of people: the flight crew, flight controllers in mission control, engineers at Goddard who would operate Hubble, support teams at various NASA centers, and communication staff managing the data flows between all these groups. During the simulations, instructors would inject problems to test the crew's ability to adapt. They would simulate equipment failures, a tool that didn't work, a bolt that wouldn't turn, an electrical connector that wouldn't mate properly. They would simulate medical emergencies, communication dropouts, and time-critical decisions. The crew had to solve these problems on the fly, deciding whether to try a different approach, use a different tool, or call for help from mission control. Often there was no single right answer. The crew had to weigh the risks and benefits of different options and make judgment calls based on incomplete information, just as they might have to do during the actual mission. These simulations weren't just for the flight crew. They were also critical for the mission control teams who would support the mission from the ground. Flight controllers practiced coordinating between the different control rooms, managing the flow of information, making real-time decisions about whether to proceed with a task or skip it if it was taking too long. Everyone learned their roles, practiced their procedures, and built the teamwork and mutual trust that would be essential when the real mission flew. The pressure on the crew and the entire mission team was immense. Everyone knew that if this repair mission failed, it would likely mean the end of the Hubble program and possibly a severe setback for NASA as a whole. There wouldn't be political or public support for a second repair attempt if the first one failed. The telescope would become a permanent testament to NASA's inability to fix its mistakes, orbiting Earth as a multi-billion-dollar embarrassment. The future of space-based astronomy, possibly the future of human spaceflight itself, depended on what these 7 astronauts and their thousands of support personnel would accomplish during 11 days in orbit. As the launch date approached in late 1993, the crew felt ready but not overconfident. They knew they had trained as hard as humanly possible. They knew they had the best tools and the best support team in the world. They knew every procedure by heart, had practiced every task hundreds of times. But they also knew that space doesn't forgive mistakes, and they were about to attempt something harder and more complex than anything any spacewalking astronauts had ever tried before. The success of their mission would determine whether Hubble would fulfill its promise or remain forever broken. In December 1993, it was time to find out. December 2, 1993. Space Shuttle Endeavour launched from Kennedy Space Center with the 7-member crew of STS-61 aboard. The weather was perfect. Florida's December skies were clear and blue. The launch itself was flawless, with the shuttle's 3 main engines and 2 solid rocket boosters performing exactly as designed. 8.5 minutes after liftoff, Endeavour was in orbit, and the crew began their carefully choreographed approach to their encounter with Hubble. The rendezvous took 2 days. The shuttle had to match orbits with the telescope, performing a series of burns to gradually raise its altitude and adjust its orbital plane. On December 4, Endeavour closed to within a few hundred feet of Hubble. Claude Nicollier, seated at the controls of the robotic arm on the shuttle's aft flight deck, took over for the final approach. Using hand controllers and multiple camera views, he carefully maneuvered the 50-foot-long arm toward the telescope. Hubble was tumbling slowly, having been put into a special safe mode for the shuttle's approach. Nicollier had to time his grapple attempt precisely, reaching out with the arm's end effector, essentially a mechanical hand with snare wires, to capture a grapple fixture on Hubble at just the right moment. There was only one good opportunity per orbit. If he missed, they would have to wait another 95 minutes to try again. The tension on the shuttle and in mission control was palpable. This was a critical moment. If the grapple failed, if the arm couldn't securely capture the telescope, the entire repair mission could be jeopardized. Nicollier moved with extreme precision, his months of training evident in every command he sent to the arm. The end effector approached the grapple fixture. Closer, closer. Then, at the perfect moment, he triggered the capture. The snare wires closed around the fixture. "Houston, we have Hubble on the arm," Nicollier reported, his voice calm despite the momentousness of the moment. Applause erupted in mission control. They had captured the telescope. Now came the next challenge, maneuvering it into the cargo bay. Nicollier spent the next hour very slowly and carefully maneuvering Hubble into position above the cargo bay. The telescope weighed 12.5 tons and was over 40 feet long. Although it was weightless in orbit, it still had enormous mass and inertia. Any sudden movement could put dangerous stresses on the arm or on the telescope's structure. Nicolia moved in tiny increments, constantly checking his camera views, consulting with the other crew members who were watching from different windows. Slowly, Hubble descended toward the cargo bay. The telescope was lowered onto a special rotating platform that had been installed in the cargo bay for this mission. This flight support system would hold Hubble securely during the repairs and could rotate the telescope to give the spacewalkers access to different sides. When Hubble finally settled onto the platform and the latches engaged, securing it in place, there was another wave of relief. The telescope was parked. The spacewalkers could now safely work on it. The real repairs could begin. The first spacewalk started early on December 5th. Story Musgrave and Jeffrey Hoffman spent hours checking out their spacesuits, pre-breathing pure oxygen to purge nitrogen from their bloodstreams, and preparing their tools. Then they opened the airlock hatch and floated out into the cargo bay. The view that greeted them was extraordinary, Hubble floating just a few feet away, its golden skin gleaming in the sunlight, Earth rolling by below at 5 miles per second. But there was no time to sightsee. They had 7 hours and 54 minutes to complete a long list of tasks. Their first major job was to install new equipment on the outside of the telescope, handrails for future spacewalkers to use, protective covers for electronics, and new magnetometers to replace ones that had been damaged by years in space. They also had to install a set of new fuse plugs that would better protect Hubble's electronics from power surges. Hoffman and Musgrave worked with practiced efficiency, their months of training evident in every movement. Each task was performed methodically. They would position themselves using foot restraints, retrieve the needed tools from a carrier attached to the shuttle or telescope, perform the work while calling out each step to mission control, then secure their tools and move to the next task. Every movement was deliberate and controlled. In microgravity, there's no friction to stop your motion, so every action has to be carefully managed to avoid drifting away or bumping into delicate equipment. One of the early challenges came when they tried to remove an equipment panel to access Hubble's interior components. The panel was held in place by small doors that were supposed to release when certain latches were activated. But the doors wouldn't budge. Years of exposure to the temperature extremes of space, cycling between extreme heat in sunlight and extreme cold in shadow, had warped the doors slightly. The thermal expansion and contraction, repeated thousands of times as Hubble orbited Earth, had caused subtle changes in the metal. Musgrave and Hoffman tried several approaches. They applied steady pressure. They tried wiggling the doors while pulling. They used different tools to try to pry them open without damaging the surrounding structure. Time was ticking away, and they had a schedule to keep. But they couldn't move forward until these doors were open. Finally, Musgrave tried a technique they had practiced in training for dealing with stuck mechanisms. He gripped the door firmly with both hands, planted his feet solidly in a foot restraint, and applied a strong, steady pull while Hoffman used a tool to manipulate the latch. The combination of forces worked. With a sudden release that nearly sent Musgrave flying backward, the door popped open. They were in. That first spacewalk accomplished all its planned objectives. When Musgrave and Hoffman came back inside after nearly 8 hours, exhausted but exhilarated, they had successfully completed every task on their checklist. One spacewalk down, 4 to go. The crew ate a quick meal, held a debriefing with mission control to discuss lessons learned, and then the spacewalkers who would go out the next day went to bed. Sleep was crucial. The next spacewalk would be even more demanding. December 6th brought Catherine Thornton and Thomas Akers outside for their first spacewalk. Their primary task was to replace one of Hubble's 2 solar arrays. The original arrays had developed a problem where they would shake and vibrate as the telescope moved in and out of sunlight, a phenomenon called jitter. The rapid heating and cooling caused the arrays to flex, and that flexing created vibrations that made it difficult for Hubble to point accurately at distant targets. The new solar arrays, provided by the European Space Agency, were stiffer and had been redesigned to eliminate the jitter problem. Removing the old solar array should have been straightforward. The array was designed to be replaceable. Disconnect some electrical cables, release some mechanical latches, and pull the array free. But space has a way of complicating even simple tasks. When Thornton and Akers tried to remove the first array, one of the latches refused to release. They tried different tools, applied force from different angles, used different techniques. Nothing worked. The latch was frozen solid. Perhaps it had been damaged by a micrometeorite impact. Perhaps it had cold welded, a phenomenon where metals can bond together in the vacuum of space. Whatever the cause, it wasn't releasing. Mission Control huddled to discuss options. They could spend more time troubleshooting, possibly hours, trying different approaches to free the latch. But that would put the rest of the mission timeline at risk. Or they could jettison the solar array, simply releasing it into space to drift away and slowly deorbit over the coming months. It wasn't the plan, and it felt wrong to abandon a piece of hardware worth millions of dollars. But Mission Control made the call: jettison the array. Better to move on and stay on schedule than to risk the entire mission by getting bogged down on one stubborn latch. Thornton activated the jettison mechanism, and the array separated from Hubble. Its golden panels slowly tumbled away from the telescope, catching the sunlight as it drifted into the darkness. It was a strange moment, watching this piece of high technology, this product of millions of dollars and thousands of hours of engineering, simply float away to become another piece of space debris. But it was the right decision. The mission had to keep moving forward. The second solar array came off more easily. Its latches released properly, and Thornton and Akers were able to hand it carefully to crew members inside the shuttle, who stowed it in the cargo bay for return to Earth. Then came the installation of the two new arrays. These were carefully removed from storage containers and attached to Hubble one at a time. Thornton and Akers connected the electrical cables, verified the connections, and then watched as the arrays deployed, unfolding like enormous golden wings on either side of the telescope. Power immediately began flowing from the new arrays. They worked perfectly. That spacewalk lasted 6 hours and 36 minutes. 2 down, 3 to go. December 7th brought Musgrave and Hoffman back outside for the third spacewalk, and this was the big one. This was when they would install WFPC-2, the new camera with built-in corrective optics. This single task would determine whether Hubble could take sharp images of the universe. Everything else could work perfectly, but if this camera installation failed, the mission would still be considered a failure. The procedure for replacing the camera had been practiced hundreds of times in the water tank, but the actual event still carried enormous tension. Hoffman and Musgrave had to open one of Hubble's major equipment bays, revealing the old wide-field and planetary camera inside. Then they had to disconnect 44 electrical connectors, each one precisely matched to carry specific signals or power. These weren't simple plugs. They were sophisticated space-rated connectors designed to maintain perfect electrical contact in the vacuum of space, resistant to temperature extremes and radiation. Disconnecting them required applying the right amount of force in exactly the right direction. Too much force could damage the connectors. Too little wouldn't release them. Working methodically, calling out each connector number as they disconnected it, Hoffman and Musgrave separated the old camera from the telescope. Then came the moment of pulling it out. The camera was the size of a baby grand piano and weighed 450 pounds on Earth. In microgravity it was weightless, but it still had mass. Moving it required careful control. Too fast and its momentum would be hard to stop. Too slow and they would run out of time. They pulled the old camera slowly out of its bay, inch by inch, making sure it cleared all the surrounding structure without scraping or bumping. When it was finally free, They handed it off to Thornton and Akers, who had positioned themselves nearby to receive it. The old camera was carefully carried to a storage container in the cargo bay and secured. It would return to Earth with them, eventually ending up in the Smithsonian National Air and Space Museum. Now came the moment of truth, installing WFPC-2. The new camera had been stored in a special protective container that maintained it at a controlled temperature. Hoffman and Musgrave retrieved it and carried it to Hubble's equipment bay. The camera had to slide into the bay with millimeter precision. Any misalignment could damage the sensitive optical and electrical connections. The bay had guide rails, but they were tight. Everything had to line up perfectly. Musgrave positioned himself with the camera, his feet secured in foot restraints that gave him a solid platform. Hoffman acted as guide, watching the alignment from a different angle and calling out corrections. Up a little, good, now a bit to the left, steady, looking good. Musgrave pushed the camera slowly forward. He could feel it sliding along the rails. There was resistance, but it felt normal, not like something was binding or catching. Still coming, halfway there, 3/4. The camera slid home with a final gentle push. They heard and felt a positive indication as it seated fully. Now came the latches. One by one, Hoffman and Musgrave engaged the mechanical latches that secured the camera in its bay. Each latch had to click into place with a positive lock. There were redundant latches to ensure the camera couldn't possibly work loose. Then came the electrical connections, 44 connectors that had to be mated precisely. Each connector was numbered and had to go into a specific receptacle. Get them wrong and at best the camera wouldn't work, at worst it could be damaged. Hoffman and Musgrave worked from a checklist, calling out each connector number as they plugged it in, waiting for confirmation from mission control that telemetry showed a good connection before moving to the next one. After what felt like hours but was actually about 90 minutes, all 44 connectors were mated. WFPC-2 was electrically connected to the telescope. Mission Control began commanding the camera to power up and run through self-checks. Telemetry streamed back to Earth. Green lights appeared on controllers' displays. The camera was alive and functioning. It was installed correctly. This was perhaps the most critical moment of the entire mission, and it had succeeded. That spacewalk lasted 6 hours and 47 minutes. 3 down, 2 to go, and so far everything was going better than anyone had dared to hope. December 8th. The fourth spacewalk brought Catherine Thornton and Thomas Akers back outside, and their task was to install CoStar, the corrective optics package that would fix the vision of Hubble's other 3 instruments. If WFPC-2 was critical, CoStar was equally so. Without it, most of Hubble's scientific instruments would still be looking through flawed optics. CoStar had to be positioned with extraordinary precision. Its tiny mirrors had to intercept light from the primary mirror at exactly the right angles. An error of even a fraction of a millimeter would ruin the correction and render 3 of Hubble's instruments effectively useless. First, Thornton and Akers had to remove the high-speed photometer, the instrument being sacrificed to make room for CoStar. The photometer had been one of Hubble's original instruments, designed to measure rapid changes in the brightness of astronomical objects with great precision. It had done good science, and many astronomers had used it for important research. Seeing it removed was bittersweet. But there was no alternative. Hubble didn't have room for both instruments, and correcting the telescope's vision took priority. Thornton and Akers disconnected the photometer's cables, released its latches, and pulled it carefully out of its bay. They handed it over to crew members inside the shuttle for storage and returned to Earth. Then came CoStar. This was perhaps the most delicate installation of the entire mission. The package was about the size of a telephone booth and weighed 600 pounds on Earth. Inside were those 5 pairs of small corrective mirrors, each precisely shaped and positioned. The package had to slide into the narrow slot where the high-speed photometer had been, threading past other components with only millimeters of clearance on each side. Any contact with the sides of the bay could damage the delicate mirrors or misalign the optical system. Thornton served as the lead for this task. She had practiced this installation more than 100 times in the water tank. She knew every movement, every potential problem, every subtle cue that would tell her if the alignment was correct. She gripped co-star firmly, her feet secured in foot restraints, Akers positioned nearby to guide and assist. Starting to insert, she called out. Mission control acknowledged. Hundreds of engineers and scientists on the ground held their breath. Thornton pushed co-star slowly forward. The package entered the bay. She could feel it sliding along guide rails. Coming in, clearance looks good on this side. She paused, adjusted the angle slightly based on Akers' guidance from his vantage point. Little more to the right, good, continuing. Her hands moved with the precision of a surgeon, feeling through her bulky gloves for any resistance or unexpected friction that might indicate a misalignment. The package slid deeper into the bay. This was the critical part. If it wasn't aligned properly, it would bind up, and they would have to pull it back out and start over. Each attempt would waste time and add to the risk of damaging something. Halfway there, still feels good, quarter way to go. Thornton's voice was calm, professional, but everyone listening could hear the intense concentration in her tone. Almost there, feels good, still good. Then, with a final gentle push, co-star seated home. Thornton felt the positive indication as it reached its final position. It's in, she reported. Latches coming next. She and Akers began engaging the mechanical latches that secured co-star in place. Each latch clicked home with a reassuring solidity. Then came the electrical connections, 48 connectors that had to be mated perfectly. They worked through the list systematically, connector by connector, waiting for confirmation from mission control that each connection showed good telemetry. When the last connector clicked into place and mission control confirmed good electrical connections across the board, there was a moment of profound relief. Co-star was in. It was connected. Preliminary telemetry showed that it was positioned correctly, that the mirrors were where they needed to be. The final proof would come when Hubble took images using the instruments that co-star corrected, but for now, everything looked good. That 4th spacewalk lasted 6 hours and 50 minutes. For spacewalks completed, 1 to go. The 5th and final spacewalk took place on December 9th. Story Musgrave and Jeffrey Hoffman floated outside one last time. Their tasks were more varied than the previous spacewalks, installing protective covers over some of Hubble's electronics to shield them from radiation, adding thermal insulation to protect against temperature extremes, replacing magnetometers and other external sensors, and performing final inspections of all the work that had been done. There was a sense of completion in the air, but also lingering tension. Until Hubble was released and its systems fully tested, nobody would know with absolute certainty if all this work had succeeded. The spacewalkers could see that everything looked right. The instruments appeared to be properly installed. The latches were secure. The electrical connection showed good continuity. But the final proof would only come when the telescope tried to observe the universe. Musgrave, the veteran spacewalker on his 6th and what would be his final spaceflight, took a moment during this last EVA to do something that had never been done before. With permission from mission control and careful coordination with the rest of the crew, he positioned himself at the very top of Hubble. There was a small work platform there, accessible only to spacewalkers, with foot restraints that allowed an astronaut to stand upright relative to the telescope. Musgrave locked his feet into these restraints and stood up. From that vantage point, 300 miles above Earth, Musgrave could see the curve of the planet below, its blue oceans and swirling white clouds stretching to the horizon. Above him was the black of space, dotted with stars that didn't twinkle because there was no atmosphere to disturb their light. And beneath his feet, secured to the work platform, was the Hubble Space Telescope, the machine they had just spent a week repairing, 43 feet of technology representing humanity's best effort to understand the cosmos. Musgrave later described this moment as one of the most profound of his life. He was standing on top of the world, literally, on a platform that humans had built and launched into orbit. He was at the interface between humanity's technological achievements and the vast universe those achievements were meant to explore. It was a moment of reflection, a pause in the midst of intense work to appreciate the magnitude of what they were attempting. Then he got back to work. There were still tasks to complete. That final spacewalk lasted 7 hours and 21 minutes. Over 5 days, the crew had completed 5 spacewalks totaling 35 hours and 28 minutes. They had performed every task on their checklist. They had overcome unexpected problems, from stuck doors to frozen latches. They had installed 2 major new instruments, replaced solar arrays and gyroscopes, and added protective equipment. They had done everything humanly possible to fix the Hubble Space Telescope. On December 10, Claude Nicollier used the robotic arm to lift Hubble out of the cargo bay and release it back into space. The procedure was the reverse of the capture days earlier, but just as delicate. Nicollier maneuvered the telescope up and away from the shuttle, then, at the planned moment, commanded the arm to release its grip. Hubble drifted away, its new solar arrays gleaming golden in the sunlight. The telescope oriented itself toward the sun, deployed its antenna to establish communications with the ground, and began running through system checks. The shuttle crew watched from their windows as Hubble grew smaller in the distance. They had done their part. They had given the telescope every chance to succeed. Now Hubble had to do its part. The crew returned to Earth on December 13, landing at Kennedy Space Center after 10 days, 19 hours, and 58 minutes in space. They were exhausted but hopeful. The real test would come in the weeks ahead, when astronomers tried to use the repaired telescope. The waiting was agonizing. It took several weeks for Hubble to be fully checked out and calibrated. Engineers systematically tested each system, each instrument, verifying that everything had survived the servicing mission intact. They commanded the telescope to point at test targets, taking images with WFPC-2 and with the instruments that relied on COSTAR for their corrected optics. The data streamed down to Earth, where teams of scientists analyzed it with intense scrutiny. The first images from the repaired Hubble were released in January 1994, and they were absolutely perfect. Sharp, clear, stunning. Stars appeared as crisp points of light with no fuzzy halos. Distant galaxies showed intricate structure that had been invisible in the blurry pre-repair images. The spherical aberration was gone, completely corrected by COSTAR and by WFPC-2's built-in corrective optics. Hubble could finally see the universe the way it was meant to. The repair mission had been a complete success. The reaction from the scientific community and the public was overwhelming. The same media that had mocked NASA's blurry telescope now praised the agency's ingenuity and determination. The same politicians who had called for investigations after the flaw was discovered now pointed to Hubble as an example of American innovation and problem-solving at its finest. Astronomers, finally able to use the telescope to its full potential, began producing discoveries that would revolutionize our understanding of the cosmos, accurate measurements of the universe's expansion rate, stunning images of star formation in distant nebulae, evidence for supermassive black holes in the centers of galaxies, and thousands of other observations that would have been impossible without the repair. But perhaps most importantly, the success of STS-61 proved something that would matter for decades to come. It demonstrated that humans could perform incredibly complex work in space. It showed that with proper training, the right tools, and enough determination, astronauts could fix anything, even something as delicate and complicated as a space telescope. This proof would be crucial, because Hubble would need servicing again. And again. And again. The first repair mission was just the beginning of a 20-year relationship between spacewalking astronauts and the telescope they kept alive. Before we continue with the remaining servicing missions, it's worth taking a deeper look at what made these spacewalks possible. The technical achievements, the instrument installations, the repairs, none of this could have happened without an extraordinary investment in training, tool development, and human preparation. The choreography of a spacewalk extends far beyond the few hours spent outside the spacecraft. It encompasses months or years of preparation, involving hundreds of people working to ensure that when the critical moment arrives, the astronauts are ready for anything. To understand the true complexity of spacewalking, you have to start with the spacesuit itself. The Extravehicular Mobility Unit, or EMU, is essentially a one-person spacecraft. It weighs about 280 pounds on Earth. It's pressurized to about 4.3 pounds per square inch, which is much less than the normal 14.7 psi we experience at sea level on Earth. This lower pressure is necessary because it allows the suit to remain flexible enough for the astronaut to move. A suit pressurized to full atmospheric pressure would be so stiff that you couldn't bend your arms or legs. You'd be frozen in one position like a balloon person. But that lower pressure creates a serious problem. If you went directly from the shuttle's cabin, pressurized to normal atmosphere, into a suit at 4.3 psi, the rapid pressure drop would cause nitrogen dissolved in your blood to form bubbles, just like opening a shaken soda bottle. This is decompression sickness, also known as the bends, and it's extremely painful and potentially fatal. The bubbles can block blood vessels, damage tissues, and cause permanent injury. To avoid this, astronauts have to pre-breathe pure oxygen for hours before a spacewalk. They typically spend about 4 hours breathing pure oxygen while the pressure in their suit or in a sealed room is gradually reduced. This process gradually purges the nitrogen from their bloodstream, replacing it with oxygen which dissolves differently and doesn't form dangerous bubbles. It's a tedious process, and astronauts on Hubble servicing missions had to go through it before every single spacewalk. Imagine spending 4 hours essentially doing nothing productive, just breathing, knowing that an exhausting 7 or 8 hour spacewalk awaits you afterward. Once in the suit and outside the spacecraft, an astronaut has about 7 hours of life support. The suit provides oxygen to breathe, removes carbon dioxide that you exhale, and circulates cooling water through tubes woven into an undergarment to prevent overheating. The human body generates a lot of heat, and in the vacuum of space, there's no air to carry that heat away. Without the cooling system, an astronaut would quickly overheat despite the cold of space. 7 hours might not sound like much time, but wearing the suit for that long is physically exhausting in ways that are hard to imagine unless you've experienced it. The gloves are perhaps the most challenging part of the suit. They have to be pressurized like the rest of the suit, which makes them stiff and resistant to bending. Imagine trying to work while wearing thick rubber gloves that have been inflated like balloons. Every finger movement requires effort. Gripping a tool tightly enough to use it means constantly squeezing against the suit's internal pressure. Your hands cramp. The fingernails press against the fingertips of the gloves, and after several hours, astronauts often develop bruised or bleeding fingernails. John Grunsfeld, who performed more Hubble spacewalks than any other astronaut, lost fingernails multiple times during his missions. He considered it a normal part of the job. The Neutral Buoyancy Laboratory, where astronauts train for Hubble missions, is one of the most remarkable training facilities in the world. The current facility at Johnson Space Center in Houston contains a pool that's 202 feet long, 102 feet wide, and 40 feet deep. It holds 6.2 million gallons of water. Inside this pool are full-scale mock-ups of spacecraft and equipment, including a complete high-fidelity mock-up of the Hubble Space Telescope. Training underwater isn't a perfect simulation of microgravity. Water has drag that space doesn't have. When you move in water, you feel resistance. In space, there's no resistance at all. Once you start moving, you keep moving until something stops you. Water also has buoyant forces that can push you in directions you don't intend to go. But despite these differences, underwater training is the best simulation available. By carefully adjusting the weights attached to a spacesuit, technicians can make an astronaut neutrally buoyant, neither sinking nor floating. In this state, the astronaut can experience something similar to the floating sensation of microgravity. For every hour of spacewalk planned for a Hubble servicing mission, astronauts typically spent 7 to 10 hours training underwater. Consider what this meant for the astronauts on STS-125, the final servicing mission. They were planning 5 spacewalks totaling about 37 hours. That meant they needed to train for roughly 260 to 370 hours underwater, spread over the 2 years of mission preparation. And that's just the time actually underwater. Add in the time spent studying procedures, attending briefings, reviewing technical drawings, practicing with tools outside the water, and the total time investment becomes staggering. During an underwater training session, an astronaut would wear a training version of the spacesuit and be lowered into the pool by crane. Safety divers would accompany them, adjusting weights as needed to maintain neutral buoyancy and standing by to provide assistance if problems arose. The astronaut would then perform the procedures they would do in space, working on the Hubble mock-up just as they would work on the real telescope. Other astronauts and instructors watched from control rooms, following along with procedures and throwing in problems to test the crew's ability to adapt. These simulations were extraordinarily detailed. The Hubble mock-up in the pool replicated every bolt, every connector, every panel and latch. It had to be precise because the astronauts were learning not just the general procedure but the specific feel of each task. They were learning that connector A17 had a slight catch when you plugged it in, that latch B23 required extra force to release, that panel C8 tended to drift away if you didn't secure it immediately after removal. This detailed tactile knowledge couldn't be gained from studying diagrams or watching videos. You had to actually do the task, over and over, until your hands remembered every detail. The tool development process for Hubble servicing was equally sophisticated. Every tool had to meet multiple requirements simultaneously. It had to work in vacuum, where lubricants could evaporate and materials could cold weld together. It had to function across a temperature range from -250 degrees Fahrenheit in shadow to +250 degrees in direct sunlight. It had to be usable by an astronaut wearing pressurized gloves that severely limited finger dexterity and tactile sensation. It had to be light enough to handle easily but robust enough to apply significant force without breaking. And it had to be tethered to prevent it from floating away while still remaining maneuverable. Consider the pistol grip tool, one of the most important tools used during Hubble servicing. This battery-powered device could drive bolts with specific torque settings, crucial when working with delicate equipment that could be damaged by over-tightening. The tool had to maintain its calibration despite temperature extremes. Its motor had to work in vacuum where normal motors might overheat due to lack of air cooling. Its battery had to perform reliably in the cold. Its trigger had to be sized so that a gloved finger could operate it, and it had to provide enough feedback through the glove for the astronaut to feel when the target torque was reached. Or consider the fastener capture plate used during the STS repair on the final mission. This was a specially designed device that fit over the electronics bay access panel. When astronauts removed screws to open the panel, each screw would fall into a small socket in the capture plate where magnets held it securely. Without this device, removing over 100 tiny screws in microgravity would have been nearly impossible. A single dropped screw could float into the telescope's optics and cause damage, or drift away into space never to be recovered. The capture plate turned a potentially disastrous task into a manageable one. Every specialized tool represented months or years of design work, prototyping, testing, and refinement. Engineers had to anticipate every way the tool might be used or misused. They tested prototypes in vacuum chambers to ensure materials wouldn't outgas or deform. They thermal cycled them repeatedly to verify they could handle temperature extremes. They tested them underwater with astronauts in pressurized gloves to verify usability. Only after passing all these tests would a tool be certified for flight. The human factors involved in spacewalking extend beyond just the physical challenges. There's also the psychological dimension. Being outside a spacecraft, with only a thin suit between you and the vacuum of space, is inherently terrifying for most people. The rational part of your brain knows you're safe as long as the suit works, but the primitive part of your brain is screaming that you're in mortal danger. Astronauts have to overcome this primal fear and remain calm and focused even when things go wrong. The psychological preparation for spacewalking involves working with psychologists and developing mental techniques for managing stress. Astronauts learn to focus on the task at hand rather than dwelling on the dangers. They practice positive self-talk, breathing exercises, and visualization techniques. They learn to recognize when stress is affecting their performance and to take brief mental breaks to reset. During the missions, flight surgeons monitor the astronauts' vital signs and watch for indications that stress levels are becoming problematic. Sleep management during Hubble missions was critical. The astronauts who would be spacewalking the next day needed as much rest as possible. The shuttle's crew compartment wasn't large, and having 7 people living in it created unavoidable noise and activity. The crew developed protocols to minimize disturbances. The non-spacewalking crew members would work quietly during the night periods, maintaining the shuttle and coordinating with mission control using hushed tones and text messages. They would prepare meals and set up equipment for the next day's EVA without disturbing their sleeping colleagues. The spacewalkers themselves often had trouble sleeping despite their exhaustion. The knowledge that the next day would bring an 8-hour spacewalk filled with critical tasks and potential dangers made relaxation difficult. Many astronauts reported lying in their sleeping bags going over procedures mentally, unable to shut off their brains despite knowing they needed rest. Flight surgeons sometimes authorized sleep medications for astronauts who were having particular trouble, but this was done cautiously because the medications had to be short-acting enough not to affect performance during the next day's spacewalk. The coordination required during a spacewalk extended far beyond just the 2 astronauts outside. Inside the shuttle, other crew members monitored life support systems, operated cameras, managed tools and equipment, and served as intermediaries between the spacewalkers and mission control. The 4th crew member, the person responsible for overall spacewalk coordination, acted as the spacewalkers' eyes and ears inside, watching displays, tracking timeline progress, and anticipating needs before they arose. On the ground, mission control rooms filled with specialists monitored every aspect of the spacewalk. There were controllers dedicated to spacesuit systems, monitoring oxygen levels, carbon dioxide removal, cooling water temperatures, and battery charge. There were controllers tracking the timeline, calculating whether tasks were proceeding quickly enough or whether adjustments needed to be made. There were engineering specialists with deep knowledge of specific Hubble systems, ready to provide guidance if unexpected problems arose. There were medical personnel watching the astronauts' heart rates, breathing patterns, and exertion levels, ready to call for a break if someone was pushing too hard. At Goddard Space Flight Center in Maryland, Hubble systems experts monitored telemetry from the telescope, watching for any indications that the spacewalk activities were affecting systems they weren't supposed to affect. They were ready to provide instant guidance on any telescope-related questions that arose. The communication between these various control centers had to be carefully choreographed. Everyone needed access to relevant information, but communication channels couldn't become so cluttered with chatter that important messages got lost. The decision-making process during spacewalks was also carefully structured. For routine tasks proceeding as planned, the spacewalkers had authority to proceed on their own. They didn't need permission for every bolt they turned. But for any significant deviation from procedures, any task that was taking much longer than expected, any situation where multiple approaches were possible, the decision would escalate to flight directors who had the overall authority to make judgment calls about how to proceed. This system worked well during the final servicing mission when Mike Massimino encountered the stripped screw while trying to repair STEES. He and his partner tried various approaches to remove the screw, but nothing worked. The decision about whether to rip out the entire handle assembly was too significant for Massimino to make alone. That call went up the chain to the flight director, who consulted with engineering teams before authorizing the aggressive approach. When Massimino tore the handle free, everyone involved knew that this had been a carefully considered decision, not a moment of frustration or improvisation. The post-spacewalk debriefings were also critical to the success of the missions. After each EVA, the crew and mission control teams would spend hours reviewing what had happened. What worked well? What took longer than expected and why? What tools were most useful? What procedures should be modified for the next spacewalk? These debriefings weren't just academic exercises. They often led to real-time changes in procedures for subsequent spacewalks on the same mission. During the first servicing mission in 1993, the crew discovered that certain tasks could be performed more efficiently than the trained procedures called for. By using slightly different body positions or tool techniques, they could save significant time. These improvements were incorporated into the procedures for later spacewalks on that same mission. The knowledge gained from each servicing mission also fed forward into the planning for future missions, creating a continuous improvement process that made each subsequent mission benefit from lessons learned earlier. The trust required between spacewalking partners was profound. Each astronaut literally held their partner's life in their hands. If one person made a mistake that damaged the other's suit, the results could be fatal. If one person became incapacitated, their partner would have to get them back inside while also managing their own safety. The pairs who spacewalked together trained together for months, learning each other's work styles, communication patterns, and tendencies. They learned when their partner needed help before being asked, when to offer encouragement, when to suggest a different approach. This trust extended to the ground teams as well. The spacewalkers had to trust that mission control was giving them good advice, that the engineering teams had done their analysis correctly, that the procedures they were following were sound. Conversely, mission control had to trust that the astronauts would follow procedures, speak up when they encountered problems, and make good decisions when circumstances demanded immediate action without time to consult the ground. The success of the first servicing mission transformed Hubble from an embarrassment into a triumph. But NASA and the astronomical community weren't content to simply maintain the telescope. They wanted to upgrade it, to take advantage of new technologies that had been developed since Hubble's initial launch. By the mid-1990s, new instruments had been built that could provide capabilities Hubble's original instruments couldn't match. The plan was to install these new instruments during regular servicing missions, gradually transforming Hubble into an even more powerful observatory. Servicing Mission 2, designated STS-32, launched on February 11, 1997, about 3 years after the first servicing mission. The crew of 7 astronauts included Kenneth Bowersox as commander. He had been pilot on the first servicing mission, Scott Horowitz as pilot, and 5 mission specialists, Stephen Hawley, Mark Lee, Gregory Harbour, Joseph Tanner, and Stephen Smith. 4 of these astronauts, Lee, Harbour, Tanner, and Smith, would perform the spacewalks as two alternating teams. The primary goals of this mission were to install two new scientific instruments, the Space Telescope Imaging Spectrograph, called STEAS, and the Near-Infrared Camera and Multi-Object Spectrometer, called NICMOS. These weren't just upgrades, they were entirely new capabilities. STEAS would allow Hubble to take spectra, breaking light into its component wavelengths of large areas of the sky simultaneously, revealing the chemical composition and physical properties of astronomical objects. NICMOS would allow Hubble to observe in near-infrared wavelengths with unprecedented sensitivity, seeing through dust clouds to reveal hidden star formation regions and detecting the faintest infrared emission from the most distant galaxies. To make room for these new instruments, two of Hubble's original instruments had to be removed, the Goddard High-Resolution Spectrograph and the Faint Object Spectrograph. Both had done excellent science over the years, but they were being replaced by instruments with significantly better performance. This was the beauty of Hubble's serviceable design finally being realized. The telescope could be continuously upgraded, keeping it at the cutting edge of astronomical technology even as that technology advanced. The mission plan called for 5 spacewalks over 5 consecutive days, following the same pattern that had worked so well during the first servicing mission. The crew had trained for months, though not quite as intensively as the first servicing mission crew. They had the advantage of learning from STS-61's experience. They knew what worked, what tools were most useful, what techniques were most effective for dealing with stubborn mechanisms. The shuttle Discovery, not Endeavour this time, rendezvoused with Hubble and captured it using the robotic arm, just as before. The telescope was secured in the cargo bay, and the spacewalks began. The first EVA, performed by Mark Lee and Stephen Smith on February 13, focused on preparing the telescope for the instrument replacements and installing new equipment. They removed several compartment doors to access the instrument bays, installed new covers to protect electronics, and replaced a fine guidance sensor, one of the systems Hubble used to point accurately at targets. The second EVA, performed by Gregory Harbour and Joseph Tanner on February 14, was when the new instruments were installed. They removed the Goddard High-Resolution Spectrograph and installed STEAS in its place. The procedure was similar to the WFPC-2 installation during the first servicing mission: disconnect cables, release latches, pull out the old instrument, install the new one, connect cables, verify connections. But even with the experience from the previous mission, it was still delicate work requiring extreme precision. STEAS slid into place smoothly, its 40+ electrical connectors mated correctly, and telemetry confirmed it was functioning. The third EVA, back to Lee and Smith on February 15, saw the installation of NICMOS. This instrument replaced the Faint Object Spectrograph. NICMOS was particularly complex because it required cooling to work properly. Infrared detectors have to be kept very cold, otherwise their own thermal emission would swamp the faint infrared signals from astronomical objects. NICMOS contained a dewar of frozen nitrogen that would keep its detectors at -321 degrees Fahrenheit. The nitrogen would gradually evaporate over the course of several years, but it would provide enough cooling for NICMOS to perform groundbreaking science. The installation went smoothly, another testament to the careful design of Hubble's serviceable systems and the training of the spacewalkers. But then something unexpected happened. During a routine inspection of the telescope's exterior, the astronauts noticed that some of the thermal insulation blankets covering parts of Hubble's skin were degraded. Years of exposure to ultraviolet radiation and thermal cycling had caused the aluminized mylar blankets to become brittle and torn in places. This wasn't immediately dangerous, but it could lead to thermal problems over time if the degradation continued. Mission Control quickly assessed the situation. The degraded insulation wasn't on the original mission plan, but they had brought spare insulation material just in case it was needed. The question was whether they had time to install it. The mission was already tightly scheduled, with barely enough time margin to handle minor delays. Adding an entire unplanned insulation repair could push them over their time limits. After extensive discussions between the crew, mission control, and engineering teams on the ground, the decision was made to add a fifth spacewalk beyond the four originally planned. Hubble and Tanner would go outside one more time to install new thermal blankets over the most severely degraded areas. This would be the first time a servicing mission had added an unscheduled EVA, a testament to both the crew's capability and mission control's confidence in their ability to adapt. The fourth and fifth spacewalks, performed over February 16th and 17th, completed the remaining planned tasks and added the thermal insulation repair. In total, the 5 EVAs totaled 33 hours and 11 minutes. When Discovery deployed Hubble back into space on February 19th and returned to Earth 2 days later, the telescope had been significantly upgraded. STES and NICMOS would go on to make spectacular discoveries, from detecting black holes by measuring the velocities of stars orbiting invisible massive objects, to peering through dust to see stars being born, to studying the atmospheres of planets orbiting other stars. Servicing Mission 2 proved that the first servicing mission wasn't a one-time feat. NASA could reliably send astronauts to Hubble, perform complex repairs and upgrades, and return the telescope to service better than it had been before. The pattern was established. Hubble would be visited every few years for maintenance and improvements. It was becoming the longest-running, most continuously upgraded space telescope in history. Hubble was originally designed with 6 gyroscopes, spinning devices that measure any rotation of the telescope. The guidance system used these gyros to detect when the telescope was drifting off target and to command the reaction wheels, internal flywheels, to correct the motion. For normal operations, Hubble needed at least 3 working gyroscopes to maintain full pointing capability. It could operate with 2 in a degraded mode, but with fewer than 2, it would have to enter safe mode, unable to perform scientific observations. By 1999, Hubble's gyroscopes were failing faster than expected. These were mechanical devices with spinning rotors, and despite being designed for the space environment, they were wearing out. 3 gyros had already failed. Then, in late 1999, a 4th gyroscope failed. Hubble was down to 2 working gyroscopes, operating in its degraded mode. If one more failed, the telescope would shut down completely. This was a crisis. The next servicing mission, Servicing Mission 3, wasn't scheduled until mid-2000, several months away. NASA didn't think Hubble could survive that long on just 2 gyros. The decision was made to split Servicing Mission 3 into 2 parts. The first part, SM-3A, would be launched as soon as possible to replace all 6 gyroscopes, ensuring Hubble's survival. The second part, SM-3B, would come later to install new instruments and perform other upgrades that had been planned for the original SM-3. Servicing Mission 3A, STS-103, launched on December 19, 1999, just before the new millennium. This was a faster turnaround than any previous Hubble mission. The crew had only a few months to prepare instead of the usual year or more. But the task was relatively straightforward: replace the gyroscopes, perform some other critical maintenance, and get Hubble back to full operational capability as quickly as possible. The crew included Curtis Brown as commander, Scott Kelly as pilot, and mission specialists Stephen Smith, Jean-Francois Clervoy, John Grunsfeld, Michael Foale, and Claude Nicollier, returning for his second Hubble servicing mission. Grunsfeld and Foale would form one spacewalking team, Smith and Nicollier the other. The mission followed the now familiar pattern: rendezvous, capture, secure Hubble in the cargo bay, perform spacewalks. The first EVA, with Grunsfeld and Foale, focused on replacing 3 of the 6 gyroscopes. The gyros were packaged in units called rate sensor units, with 2 gyros per unit. Replacing a rate sensor unit meant opening an equipment bay, disconnecting cables, removing the old unit, installing a new one, and reconnecting everything. The procedure had been practiced extensively, and it went smoothly. The second EVA, with Smith and Nicolia, replaced the other 3 gyroscopes and also replaced one of Hubble's fine guidance sensors. These sensors, which tracked guide stars to keep the telescope pointed accurately, were also wearing out and needed replacement. The third EVA, back to Grunsfeld and Foale, replaced Hubble's computer with a faster, more capable model, installed a new solid-state digital recorder to replace an aging tape recorder that had been causing problems, and replaced a transmitter used to send data back to Earth. All 3 spacewalks went remarkably smoothly considering the rushed preparation time. The total EVA time was 24 hours and 33 minutes over 3 days. When Discovery deployed Hubble on December 25, Christmas Day 1999, the telescope was healthy again, with 6 new gyroscopes and several other upgraded systems. It could return to full scientific operations, and the astronomical community breathed a collective sigh of relief. The crisis had been averted. SM-3A demonstrated NASA's ability to respond quickly when Hubble faced urgent problems. The servicing mission architecture, with astronauts able to travel to the telescope and perform repairs, had proven its worth once again. Hubble was saved, able to continue its groundbreaking observations while awaiting the next planned servicing mission. With Hubble's gyroscope crisis resolved, NASA could proceed with the second half of servicing Mission 3. SM-3B, designated STS-109, launched on March 1, 2002. This mission would install new instruments and perform upgrades that would give Hubble new capabilities and extend its operational life. The crew included Scott Altman as commander, Dwayne Carey as pilot, and mission specialists Nancy Curry, John Grunsfeld, returning for his second Hubble mission, Richard Linhan, James Newman, and Michael Massimino. Grunsfeld would lead the spacewalking team, partnering with Linhan on some EVAs and with Massimino on others. Newman and Massimino would form the other team. The primary goal was to install the Advanced Camera for Surveys, called ACS. This new camera would replace the Faint Object Camera, the last remaining original instrument from Hubble's launch. ACS was a significant upgrade, with a wider field of view and better sensitivity than any of Hubble's previous cameras. It would be able to survey large areas of the sky quickly, making it ideal for projects like studying the large-scale structure of the universe or searching for gravitationally lensed galaxies. The mission also planned to install new solar arrays. Hubble's second-generation arrays, installed during the first servicing mission in 1993, were working fine but were larger than they needed to be. New, more efficient solar cells had been developed that could generate the same amount of power from smaller arrays. Installing these new arrays would reduce Hubble's drag from the tenuous atmosphere at its orbital altitude, reducing the rate at which it gradually lost altitude and fell toward Earth. 5 spacewalks were planned, alternating between the 2 astronaut teams. The first EVA, with Grunsfeld and Linhan on March 4, replaced one of the solar arrays. The old array was removed and the new one installed, unfolding smoothly and immediately beginning to generate power. The second EVA, with Massimino and Newman on March 5, replaced the other solar array. The third EVA, back to Grunsfeld and Linhan on March 6, was the big one, installing ACS. The procedure was similar to previous instrument installations: remove the Faint Object Camera, install ACS in its place, connect 40+ electrical connectors, verify everything was working. But there was always tension during these installations. These were one-of-a-kind, irreplaceable instruments worth hundreds of millions of dollars. A single mistake during installation could doom the instrument to failure. The astronauts moved with extreme care, every action deliberate and controlled. ACS slid into place perfectly. Its connectors mated correctly. Telemetry showed good electrical connections. When engineers commanded ACS to power up and run self-tests, it responded perfectly. The installation was a success. Hubble had a new eye that would allow it to see the universe with unprecedented breadth and clarity. The fourth and fifth EVAs performed additional maintenance, replacing another power control unit, installing cooling equipment for the advanced camera, and adding more protective coverings to shield against radiation. All 5 spacewalks were completed successfully, totaling 35 hours and 55 minutes. When Columbia, the shuttle used for this mission, deployed Hubble back into space on March 9 and returned to Earth 3 days later, the telescope had been transformed once again. ACS would go on to take some of the most iconic images in Hubble's history, including deep field observations that revealed thousands of galaxies in tiny patches of seemingly empty sky, showing the universe's evolution over billions of years. SM-3B continued the pattern of regular Hubble upgrades. Every few years, astronauts would visit the telescope, fix whatever was failing, and install new capabilities. Hubble was more powerful in 2002 than it had been at launch in 1990. And there was one more servicing mission yet to come, the most ambitious and challenging of them all. After SM-3B in 2002, the next servicing mission was scheduled for 2005. But then disaster struck. On February 1, 2003, Space Shuttle Columbia broke apart during reentry, killing all 7 crew members. The accident, caused by foam insulation breaking off the external tank during launch and damaging the shuttle's heat shield, led to the grounding of the entire shuttle fleet. NASA launched an intensive investigation into the accident and began working on changes to prevent such a disaster from happening again. But the investigation also raised serious questions about shuttle safety in general. The foam shedding problem had been known for years but had been dismissed as an acceptable risk. Now that risk had killed 7 astronauts. Should the shuttle program continue at all? In the aftermath of the Columbia accident, NASA Administrator Sean O'Keefe made a controversial decision. He cancelled the final planned Hubble servicing mission. His reasoning was based on safety. If a shuttle traveling to the International Space Station had a problem, the crew could shelter on the station while another shuttle was prepared for a rescue mission. But Hubble orbited at a different altitude and inclination than the ISS. A shuttle going to Hubble couldn't reach the space station if there was a problem. If the heat shield was damaged during launch, the crew would be stranded with no safe haven. O'Keefe determined that the risk was unacceptable. The Hubble servicing mission was cancelled. The astronomy community reacted with dismay and anger. Without another servicing mission, Hubble would gradually fail as components wore out. The gyroscopes would fail again, just as they had before SM-3A. The batteries, which had been in space since 1990, would continue degrading until they could no longer hold a charge. The instruments, subjected to years of cosmic radiation and temperature cycling, would eventually experience electronic failures. Within perhaps 5 years, maybe less, Hubble would become inoperable. Its mission would be cut short not by any flaw in the telescope itself but by a decision not to service it. Decades of scientific potential would be lost. The reaction was swift and passionate. Prominent astronomers organized letter-writing campaigns, encouraging scientists and citizens to contact their congressional representatives. They testified before Congress, making the case that Hubble was too valuable to abandon. They appeared on television news programs, in newspaper opinion pieces, and at public forums, arguing that the scientific value and the symbolic importance of Hubble justified the risks of one final servicing mission. The arguments were compelling. Hubble had become more than just a scientific instrument. It had become a cultural icon, its images displayed in museums, schools, homes, and workplaces around the world. The public had followed Hubble's redemption story from the flawed telescope to the triumphant first repair to the spectacular images that followed. There was genuine public affection for Hubble. Abandoning it felt wrong to many people, not just to astronomers. Astronauts, including several who had flown to Hubble before, volunteered publicly to fly the mission despite the risks. John Grunsfeld, who had spacewalked at Hubble twice already, spoke eloquently about the importance of the mission and his willingness to accept the risks involved. Other astronauts made similar statements. The message was clear: the astronaut corps wasn't afraid of this mission. If NASA was willing to fly it, there would be no shortage of volunteers for the crew. The debate continued for over 2 years, with passionate arguments on both sides. Those supporting the cancellation pointed to the very real safety concerns. The Columbia accident had proven that foam strikes could be fatal. Until that problem was fully understood and mitigated, how could NASA justify risking another crew? And even with improvements, a Hubble mission would still be riskier than an ISS mission because of the lack of a safe haven option. Was Hubble worth risking 7 more lives? Those opposing the cancellation argued that all spaceflight involved risk and that eliminating all risk was impossible. The question wasn't whether there was risk, but whether the benefits justified accepting that risk. They pointed out that the astronauts themselves, the people who would actually face the risks, were willing to fly the mission. Who was the administrator to override their judgment? They also argued that letting Hubble die would send a terrible message about America's commitment to science and space exploration. Then, in 2006, Michael Griffin replaced Sean O'Keefe as NASA administrator. Griffin brought a different perspective on risk. He had a strong technical background, with degrees in aerospace engineering, electrical engineering, civil engineering, physics, and business administration. He understood spacecraft systems and orbital mechanics at a deep level. He also had a philosophical approach to risk that differed from O'Keefe's. Griffin believed that human spaceflight inherently involved risk and that eliminating all risk was neither possible nor desirable. The question wasn't whether to accept risk, but how much risk was acceptable in service of what goals. He began reviewing the possibility of flying one final Hubble servicing mission, looking at what could be done to mitigate the risks to acceptable levels. His review concluded that the risks could indeed be managed. NASA had made significant improvements to the shuttle system since the Columbia accident. They had developed new inspection techniques using cameras and sensors to examine the heat shield in detail while in orbit. They had improved procedures for repairing heat shield damage if it was discovered. They had restricted launches to times when lighting conditions allowed good photography of the external tank during ascent, making it easier to see if foam shedding occurred. Most importantly, Griffin approved a rescue mission capability specifically for the Hubble mission. Another shuttle would be prepared on a second launch pad, ready to fly a rescue mission if needed. If the Hubble mission shuttle suffered heat shield damage that couldn't be repaired, the crew could wait in orbit while the rescue shuttle was launched. The rescue shuttle would rendezvous with a damaged shuttle, and the crew would transfer over via spacewalk. This rescue option wasn't perfect, it would be risky in its own right, and it would require the crew to potentially wait in orbit for weeks in a damaged shuttle. But it provided an option that didn't exist before. After extensive analysis and consultation with engineers, safety experts, and the astronaut office, Griffin announced in October 2006 that the final Hubble servicing mission would proceed. The announcement was met with cheers from the astronomical community and relief from NASA personnel who had been advocating for the mission. Hubble would get one more chance, one final visit from human hands, one last opportunity to be upgraded and repaired for the remainder of its operational life. Scientists organized letter-writing campaigns, testified before Congress, appeared on television news programs arguing for one final Hubble mission. They pointed out that Hubble had become humanity's most productive scientific instrument, responsible for revolutionizing astronomy. They argued that the scientific value and the symbolic importance of Hubble justified the risks. Astronauts, including several who had flown to Hubble before, volunteered to fly the mission despite the risks. The debate continued for over 2 years. Then, in 2006, Michael Griffin replaced Sean O'Keefe as NASA administrator. Griffin had a different perspective on risk. He believed that human spaceflight inherently involved risk and that eliminating all risk was impossible. The question was whether the benefits justified the risks, and whether the risks could be managed to acceptable levels. Griffin began reviewing the possibility of flying one final Hubble servicing mission. After extensive analysis, Griffin announced in October 2006 that the final Hubble servicing mission would proceed. NASA would take extraordinary precautions. Another shuttle would be prepared on a second launch pad, ready to fly a rescue mission if needed. The crew would perform detailed inspections of the heat shield using cameras and sensors. Additional thermal protection would be added to vulnerable areas of the shuttle. Every possible precaution would be taken. But the mission would fly. The crew for this final mission, designated STS-125, included Scott Altman as commander, returning for his second Hubble mission, Gregory Johnson as pilot, and mission specialists Megan MacArthur, John Grunsfeld, returning for his third Hubble mission, Michael Massimino, his second Hubble mission, Andrew Fustel, and Michael Good. Grunsfeld, Massimino, Fustel, and Good would perform the spacewalks as 2 teams. The goals for this mission were ambitious. Install 2 new instruments, the Wide Field Camera 3 and the Cosmic Origin Spectrograph. Repair 2 failed instruments, the Advanced Camera for Surveys and the Space Telescope Imaging Spectrograph, both of which had suffered electronic failures and stopped working. Replace all 6 gyroscopes again. Replace the batteries. Replace a fine guidance sensor. Install new thermal insulation. The mission would require 5 spacewalks and would push the limits of what could be accomplished in a single servicing mission. The crew trained for over 2 years, longer than any previous Hubble crew. They practiced the instrument installations, which were now familiar procedures. But they also practiced the repairs of ACS and STEs, which were unprecedented. These instruments had never been designed to be repaired in orbit. They had electronics deep inside them that were supposed to be sealed and inaccessible. To fix them, astronauts would have to remove panels that were never intended to be removed in space, reach inside with special tools, and replace failed circuit boards. New tools were developed specifically for these repairs. There were power tools designed to remove dozens of tiny screws. There were fastener capture plates to prevent screws from floating away when removed. There were special handles and positioning devices to allow astronauts to work inside the tight confines of the instrument bays. The crew practiced these repairs hundreds of times in the water tank until they could perform them reliably. Launch was initially scheduled for October 2008, but it was delayed when a critical data handling unit on Hubble failed in September. NASA decided to refurbish a spare unit that had been in storage for years and to include replacing this unit as an additional task on the servicing mission. This delayed launch to May 2009, but it meant that the mission could fix this new problem in addition to all the planned tasks. May 11, 2009. Space Shuttle Atlantis launched from Kennedy Space Center carrying the crew of STS-125. On another launch pad, Space Shuttle Endeavour sat ready for a rescue mission if needed. The weather was perfect. The launch was flawless. The rescue shuttle would not be needed. 2 days later, Atlantis rendezvoused with Hubble for the 5th and final time. Megan MacArthur, operating the robotic arm, captured the telescope and secured it in the cargo bay. For the last time, Hubble was parked in a shuttle cargo bay awaiting the attention of spacewalking astronauts. The crew knew this was historic. This would be the last time human hands touched Hubble. Whatever they accomplished on this mission would have to be enough to keep the telescope operating until it was eventually retired, probably sometime in the 2020 timeframe. The first spacewalk, on May 14, was performed by John Grunsfeld and Andrew Fjustel. Their primary task was to install the Wide Field Camera 3, replacing WFPC-2, the camera that had been installed on the first servicing mission 16 years earlier. WFPC-2 had been extraordinarily productive, taking many of Hubble's most famous images. But after 16 years, its technology was dated. WFC-3 would observe in ultraviolet, visible, and near-infrared wavelengths with far better sensitivity and resolution. The installation followed the now-practiced routine: disconnect cables, remove old camera, install new camera, connect cables. But even though it was the 5th time astronauts had performed a major instrument installation on Hubble, it was still nerve-wracking. WFC-3 slid into place perfectly. Its connectors mated properly. Telemetry confirmed good electrical connections. One new instrument installed. That EVA lasted 7 hours and 20 minutes. The second spacewalk, on May 15 with Massimino and Good, installed the Cosmic Origin spectrograph, replacing COSTAR. COSTAR had served its purpose brilliantly, correcting Hubble's optics for 16 years. But it was no longer needed. All of Hubble's current instruments had their own corrective optics built in. The space COSTAR occupied could be better used by a new instrument. The Cosmic Origin spectrograph would study the large-scale structure of the universe by analyzing ultraviolet light from distant quasars, revealing the cosmic web of gas that connects galaxies. The COS installation went smoothly. But then Massimino and Good faced their other major task: repairing the advanced camera for surveys. ACS had failed in 2007 when its power supply died. The repair required removing 32 tiny screws, each smaller than a shirt button, to access the failed electronics. A special screw removal tool was used, with each screw carefully captured to prevent it from floating away. Once the panel was removed, the astronauts had to install a new power supply module, essentially bypass the failed components with new electronics. The repair was delicate work requiring extreme precision and patience. One dropped screw, one fumbled connection, could doom the repair. But Massimino and Good worked through the procedure methodically. After several hours of painstaking work, the new power supply was installed. The panel was replaced, the screws secured. When Mission Control commanded ACS to power up, it responded. The repair was successful. An instrument that had been dead for 2 years was alive again. That spacewalk lasted 7 hours and 56 minutes. The third spacewalk, on May 16, brought Grunsfeld and Fjustel back outside to repair the Space Telescope imaging spectrograph. STEES had failed in 2004 when its power supply died, a different failure than ACS but with similar implications. The repair required removing even more screws, 111 of them, to access the electronics bay. A special fastener capture plate was used to prevent the screws from escaping. This repair would prove to be the most challenging task of the entire mission. The screws came out smoothly, and the panel was removed. But when Fjustel tried to remove the failed circuit board, it wouldn't come out. Something was holding it in place. He and Grunsfeld tried different approaches, different tools, different angles. Nothing worked. They were running out of time. Each spacewalk had a maximum duration limited by the life support capacity of the spacesuits. They couldn't stay out indefinitely troubleshooting this problem. After consultation with Mission Control and engineering teams on the ground, they made the decision to leave the repair for the next spacewalk. They replaced the panel, secured the screws, and came inside. That night, engineers analyzed the problem and came up with a new approach. The circuit board was being held by a grounding strap that hadn't been visible in the diagrams. On the next spacewalk, they would have to remove this strap before they could extract the board. That third EVA lasted 6 hours and 36 minutes. The fourth spacewalk, on May 17th, was one of the longest ever performed. Massimino and Good went back to Steez to complete the repair. Armed with new knowledge about the grounding strap, they removed the panel again and worked on extracting the circuit board. But now they encountered a new problem. One of the screws on a handle that had to be removed had stripped threads. Massimino tried every technique he could think of to remove the screw. Nothing worked. Mission Control consulted with engineers. Time was running out. Finally, they made a bold call: if the screw wouldn't come out, remove the entire handle, ripping it out if necessary. Massimino gripped the handle firmly and pulled. The handle resisted. He pulled harder, using all his strength. Suddenly, with a jerk that nearly sent him tumbling, the handle tore free, taking its mounting hardware with it. The path was now clear. Massimino and Good removed the failed circuit board and installed a new one, bypassing the failed power supply. They reassembled everything, working as quickly as they dared while still being careful not to make mistakes. When they finally commanded Steez to power up, the moment was tense. This repair had taken 2 spacewalks and had required improvisation when things went wrong. Had it worked? Telemetry streamed back. Green lights appeared on displays in Mission Control. Steez was alive. The repair was successful. Another dead instrument had been brought back to life by human hands. That fourth spacewalk lasted 8 hours and 2 minutes, making it the 6th longest spacewalk ever performed. The 5th and final spacewalk, on May 18, brought Grunsfeld and Fustel outside one last time. Their tasks included replacing all 6 gyroscopes with new units, installing fresh batteries to replace the originals that had been in space for 19 years, installing new thermal insulation, and attaching a soft capture mechanism that would allow a future robotic spacecraft to safely deorbit Hubble at the end of its life. This final spacewalk had a sense of ceremony about it. Grunsfeld and Fustel knew they were the last humans who would ever touch Hubble. When they were done, when they came back inside and closed the airlock hatch for the last time, that would be it. Hubble would be on its own, maintained by the work they and their colleagues had done over 5 missions spanning 16 years, but no longer serviceable by human hands. They worked through their tasks with the efficiency that came from decades of collective experience across all the servicing missions. The gyroscopes were replaced. The batteries were installed. The insulation was added. The soft capture mechanism was attached. Every task was completed. That final spacewalk lasted 7 hours and 2 minutes. Over 5 days, the crew had completed 5 spacewalks totaling 36 hours and 56 minutes. They had installed 2 new instruments, repaired 2 dead instruments, replaced critical components, and added systems that would allow Hubble to continue operating for years to come. They had accomplished everything they set out to do and more. On May 19, Megan MacArthur used the robotic arm to lift Hubble out of the cargo bay one final time. The telescope, upgraded and repaired, was released back into space. It oriented itself toward the Sun, its new solar arrays gleaming. It established communications with the ground. All systems reported healthy. Hubble was ready for the next chapter of its mission. Atlantis returned to Earth on May 24 after 12 days, 21 hours in space. The crew received a hero's welcome. They had accomplished what many thought impossible. They had given Hubble years of additional operational life. The instruments they installed and repaired would allow the telescope to make discoveries that hadn't even been imagined when the mission was planned. In the years following the final servicing mission, Hubble continued to exceed all expectations. The Wide Field Camera 3 proved to be an extraordinarily powerful instrument, capable of taking some of the deepest, most detailed images of the universe ever captured. The cosmic origin spectrograph revolutionized the study of the intergalactic medium. The repaired advanced camera for surveys and space telescope imaging spectrograph resumed their groundbreaking work. Hubble discovered dark energy, the mysterious force accelerating the universe's expansion. It measured the universe's age and expansion rate with unprecedented precision. It captured images of galaxies as they appeared when the universe was less than 1 billion years old. It watched stars being born in stellar nurseries and dying in supernova explosions. It detected the atmospheres of planets orbiting other stars. It revealed the supermassive black holes lurking in the centers of galaxies. It provided evidence for the existence of dark matter. The list of discoveries goes on and on. More than 1.7 million observations. More than 18,000 scientific papers published using Hubble data. Hundreds of thousands of images, many of which have become iconic cultural symbols. Hubble has been humanity's most productive scientific instrument, transforming our understanding of the cosmos in ways that would have been impossible without it. But perhaps Hubble's greatest legacy is what it demonstrated about human capability in space. 5 servicing missions. 32 astronauts who flew to Hubble. 20 astronauts who spacewalked to repair and upgrade it. 165 hours and 45 minutes of total EVA time. Over 150 specialized tools developed. Thousands of people on the ground supporting each mission. It was an unprecedented demonstration of human ingenuity, determination, and courage. The servicing missions proved that humans could work in space with the precision required for the most delicate tasks. They showed that proper training, the right tools, and careful planning could overcome almost any challenge. They demonstrated that the ability to send humans to repair and upgrade space assets was valuable beyond measure. Without those servicing missions, without the astronauts who risked their lives to fix and improve Hubble, the telescope would have been an expensive failure. Instead, it became one of humanity's greatest scientific achievements. The choreography of those spacewalks, the ballet performed 300 miles above Earth by astronauts in bulky spacesuits working with millimeter precision, represents some of the most impressive accomplishments in the history of space exploration. Every motion was practiced hundreds of times. Every tool was carefully designed for its specific purpose. Every procedure was rehearsed until it became automatic. And when unexpected problems arose, as they always did, the astronauts adapted, improvised, and found solutions. As of this recording, Hubble continues to operate, now over 30 years after its initial launch. The instruments installed on that final servicing mission in 2009 continue to return spectacular data. The gyroscopes, batteries, and other components replaced during the 5 servicing missions continue to function. The telescope is gradually losing altitude, slowly spiraling toward Earth due to drag from the tenuous upper atmosphere. Eventually, probably sometime in the 2020 timeframe, it will be deliberately deorbited, commanded to re-enter Earth's atmosphere and burn up over an empty area of ocean. But until that day comes, Hubble keeps watching the universe. Every day, it performs observations scheduled by astronomers around the world. Every day, it returns data that expands our knowledge of the cosmos. It stands as a monument to what humans can achieve when they combine scientific vision, engineering excellence, and the courage to venture into the hostile environment of space to build, repair, and maintain the tools of discovery. So if you found this journey through the Hubble repair missions interesting, consider subscribing to the channel. Hit that like button if you enjoyed learning about the spacewalk choreography that saved humanity's greatest telescope. There are more stories of exploration and discovery to come, more tales of humans pushing the boundaries of what's possible. The Hubble missions show us that with determination, skill, and teamwork, we can accomplish the seemingly impossible. We can fix problems hundreds of miles above Earth. We can build tools that reveal the deepest secrets of the universe. We can reach into the cosmos and bring back knowledge that changes how we understand our place in existence. And that's worth celebrating, worth sharing, worth remembering as we continue our species' greatest adventure, the exploration of the universe we call home.